Welcome to HC26. Tutorial 2, Internet of Things.
Okay, everyone. Welcome to the second tutorial of HotChips 2014.
I'll clips on your bill.
Okay, sorry. So, as you know, IoT is a hot topic these days, and lots of work and research is going on in that area. We're expecting to see in the next maybe 3 or 5 years, 10 of billions or like 100 of billions of these tiny devices deployed in things around us. Right? And thinking about it, like traditional methods for powering and connecting SoCs or computing systems won't work, won't scale for that number of units and that tiny devices. So there are lots of challenges for powering and connecting these devices. So today we have 4 speakers, experts in this field, and they're going to be talking about these challenges for powering, number 1, and number 2, connecting these devices. So that's how we organize this tutorial. We're going to have 2 talks about powering IoT. And then we have a short break. After the break, we are going to have 2 talks about connectivity for IoT devices. And if time allows, we're going to have a short panel, open panel for questions. Okay, so let me just quickly introduce the first speaker. Yogesh Ramadass is a lead circuit design engineer at Texas Instruments. His expertise are next generation energy harvesting and low power DC-DC converters. So he has received lots of distinguished awards recently. Just to mention 2 of them, the President of India Gold Medal in 2004, and EE Times Innovator of the Year last year. He's got a master and PhD from MIT and a bachelor degree from IIT. With that, please welcome the first speaker, Yogesh Ramadass.
Thanks. Okay, thank you, Behnam, and good afternoon, everyone. My name is Yogesh Ramadass, and I'm from Texas Instruments, and I'm very excited to be here talking about the Internet of Things and how to power them. Okay. Okay, there we go. Perfect. All right. So, sophisticated battery-operated and self-powered systems have found diverse applications recently, existing as autonomous or handled objects in every environment around us, and in some cases even within us. So for almost all of these systems, energy efficiency, long operational lifetimes, and low cost are of paramount importance. So the energy efficiency of the ICs, the integrated circuits within these systems, play a major role in determining the size, the weight, and the operating lifetime of these systems. And accordingly, extensive research and development effort has gone on in trying to reduce the power consumptions of the ICs themselves and how efficiently we're going to deliver the power to these ICs. So if we take a look at a standard subsystem of how an IoT node is going to look like. So we've got sensors which are detecting things of our interest. And these sensors feed their signals onto the analog front ends, which then process these locally and then digitize them, from which the processor tries to understand what is it that it's sensing, locally processes the data, and then radios it out to a central hub from where the user can make the recommended decisions. The entire node would be powered by an energy subsystem. Now, it could be battery-powered, or it could be self-powered. And we'll talk about these systems in the next few slides. So over the last few years, significant research and industry efforts have gone on into decreasing the power consumption of each of these sub-blocks. So I've just tabulated some of the recent numbers for a front-end instrumentation amplifier, some for ADCs, the microcontrollers. And if you look at it, I mean, the radio still dominates the power, but primarily ultra-low voltage operation, parallelism, local processing of information, and aggressive duty cycling has brought down the power consumption of these blocks significantly. To just take a look at one of these blocks, I've shown an example of an analog to digital converter here. We're defining a factor called alpha, which is the activity factor. Basically, it says how often the data from a cycle-to-cycle basis varies compared to the full-scale signal. Now, if you look at the subsystems of our interest, in this case, an ECG signal or a vibration signal coming from a motor monitoring unit, the activity of these signals are very, very low. So in this work, the author basically has looked into the activity of these signals and figured out, okay, the traditional way of doing analog to digital conversion with this SR ADC is very power hungry. I mean, it doesn't really utilize the characteristics of these signals. And so he's proposed a way to do an LSB first, a predictive algorithm, and then he can obtain significant savings in power. So that's just one of the examples of using the characteristics of the system we're operating in to reduce power of the blocks. The next case, I'm showing how, as we saw before, the radio consumes quite a bit of power in these systems. So how do we reduce the total power consumption of, or how do we minimize the number of transactions we do through the radio? So in this case, I'm showing a system where it's an epileptic seizure onset detection system. So if you look at the traditional system, the power consumed for capturing the data is around 75 microwatts, but the radio power is close to 1.8 milliwatts, so that completely dominates, and it becomes unusable in a self-powered situation. But if you're able to just spend some amount of energy to locally process the data, figure out from the characteristics of the signal that you're getting that what is really important to transmit, then you can see by spending a little amount of power, you reduce the power consumption of the radio significantly, and now your overall power of the system is around 120 microwatts. So this is a paradigm known as computation as a communication trade-off. I'm sure the future speakers are going to talk about these. So I'm just pointing these out to let you know that a lot of work has gone on to bring the power of the systems of interest low enough where now we're able to talk about self-powering these systems, basically operating them without the need for a battery. So almost all of these systems have the traditional characteristics of low data rate, very low duty cycle of operation, and eventually ultra-low power. So be it for convenience, as in the case of a solar keyboard or electronic shelf tabling shelf tags, or whether it's very hard to reach in the case of implantables or on oil pipelines, or for environmental awareness in the case of smoke detector, motor monitoring, occupancy sensors, it is convenient for us to try to replace the battery and power these systems from the ambient energy that's available. So through the course of this tutorial, we're going to talk about how do these energy sources look like, what the characteristics are. We'll look at how to take this energy and store them in the storage mediums. And then the circuits that help us in transferring this energy from the energy source onto the storage medium and eventually to the load circuits that need to use these. And towards the end of the talk, I'll show you some of the practical systems that can be built with these and then summarize. So before jumping into self-powered systems, let's look at how a typical battery-operated system looks like from the power delivery point of view. We've got the battery, and we've got the load circuits, the AFE, the radio, the microprocessor, and sensor. Each of these may be operating from a different voltage rail, and all of them are powered from the battery. And then the regulator is the one which converts the voltage from the battery onto the load circuits. There may be multiple of them, or they could be sharing. And in this system, the two other blocks are, the moment you use a battery, you need to protect it from, say, under voltage events or over temperature events, and then you need a power good indicator to tell the load that, okay, the battery is good enough, it's charged enough that you can power. So if you look at this system, I mean, the main point to note is a battery is an energy source. So when the load is not requiring power, you can pretty much shut down the system and the battery goes into its self-discharge state, and that's the only power lost. But if you look at the typical energy density within a battery, I'm quoting a centimeter cube lithium ions, around 2,800 joules, and that's equivalent to a year at 100 microwatts of power. So if you're talking about storing these sensors all around and not worrying about whether they're operational or not, then we want to look at self-powered solutions. So if you look at a self-powered system, this is how the power delivery part of it looks like. The load circuits and the regulators remain the same. In this case, instead of being powered directly from the battery, now they're going to be powered from ambient energy sources, could be light, heat, or vibration. Or in specific cases, you may put targeted RF energy onto these systems, though it's not clearly self-powered in that sense. The energy from the harvesters are then taken, and there's dedicated power management circuits that take this energy and store it in a battery. It could be a rechargeable battery or a supercapacitor. And then the energy from that storage is then given to the load through the regulators. Now, in this case, not only do we need undervoltage and over-temperature protection, we also need over-voltage protection because you're charging a storage medium and you need to protect the circuits. The main blocks on the interface side is the charger itself, which takes in the energy from the harvester and puts it into the storage. There's very specialized circuits, say for AC harvesters like vibration and RF, you need rectification circuits. And then there's a block called the cold start block. So in a self-powered system, if it's just being shipped from a factory, of course there's not going to be much energy on the storage medium. So how do all these circuits come up and start operating? And so the block that does that is the cold start block. We'll talk about it later. The key difference now between a battery-operated system and an energy harvesting system, as we saw, the battery was an energy source. The energy harvester is actually a power source. So if you're not trying to extract power from the harvester, you're basically losing all that power. It's not like it's stored as in a battery. So the fundamental difference being then this energy management interface circuit needs to be always on, trying to look at how much amount of power is coming from the harvester and try to maximally extract the power available because it's a high impedance system. And so the energy management circuits now need to be highly tuned to the harvester that we're working with. And so we'll talk about how to do that through the MPPT circuits and stuff. So let's now start looking at how the sources look like. So one of the easiest ways to harvest power is from the ambient light energy. All of you are familiar with this, and basically consists of a solar cell, which is just a PN junction diode. And when light impinges on it, photons with enough energy are going to knock out electron-hole pairs, and the built-in junction is going to separate them out, and you're going to get a potential. And if you close the circuit, you're going to get current flow in that circuit, and that current is going to be, the short circuit current, is going to be proportional to the amount of irradiation you're going to put on. It's impinging on the solar cell. So from a circuit point of view, it's a very simple equivalent circuit. You've got current proportional to the light, and we've got the inbuilt junction. And we've got to take this energy out in the most efficient of ways. There are many different types of solar cells available, each with its own particular characteristics, crystalline being quite efficient, but not so efficient in indoor situations where the amorphous cells do much better. And there's also recent innovations in dye-sensitized solar cells, which are much more flexible, and you could put it in different form factors and such. And they provide pretty good efficiencies for indoor conditions of 200 to 400 lux or so. So if you look at the typical power that comes out of these solar cells, here I've shown a case of 7 solar cells in series. So the bottommost curve would be at indoor light conditions, and as you keep increasing the light intensity, the power goes up super linearly. And so if you look at average powers that we're talking about, a few tens of microwatts for indoor light conditions of around 200 lux intensity. And if you go into bright sunlight, you can typically get a few milliwatts of power out of these cells per centimeter square of the cell. Okay. The other thing to note is also, as I said, these are high impedance devices. So if you keep them open, they're going to operate at its open circuit voltage. If you completely load the cell, it's going to go down to its short circuit current. And in between these two extremes is where the maximum power you can get out of the cell is. It's called the maximum power point, and I've shown it with the red dots in the curves. And as you can see, with varying intensity and stuff, the maximum power point moves. And ideally, in our system, we would like to operate at that particular point and extract the maximum power out of the solar cell. It's as simple as that. Moving on, that was a brief description of solar cells. Thermoelectric generators basically used to harvest ambient heat energy. And it's the basic unit of the thermoelectric energy harvester. It operates on the Seebeck effect. It's a P and N thermocouple, which consists of a P-type material electrically in series with an N-type material, typically bismuth telluride. And so when heat is applied, or heat energy, temperature difference is applied across the two plates of this material, heat flows from the hotter side to the colder side. And in the process, the heat is actually transferred through electrons in the N side and holes in the P side. And so if you close the circuit, you actually get a voltage differential at its open circuit, which is very closely proportional to the amount of temperature difference applied across the plates. So if you look at a typical thermocouple, now it's going to generate very, very little amount of voltage. You look at it, it's 0.2 millivolts. It's 200 microvolts per Kelvin of temperature difference. So that's pretty much unusable for circuits. So to build up this voltage, a lot of these cells are placed electrically in series, but thermally in parallel to form a thermopile, as shown in the figure here. And that now can increase the voltage from which circuits can operate off. So if you look at the typical characteristics, here's one thermoelectric generator from a company called Tellurix. These are commercially available harvesters that you can buy. So this has got 127 of these PN legs in series. But even after doing that, you only get 23 millivolts per Kelvin of temperature difference. So if on a typical human body, you're probably experiencing around 2 to 3 Kelvin of temperature difference. In machines, more than 10 to 20 degrees or so. And so if you look at the voltage now, you're expecting around 50 millivolts for a wearable situation, and around 200 to 300 millivolts in an industrial setting. And the power also scales, in fact, quadratically with the temperature difference. We're talking about around 30 to 40 microwatts per centimeter square on a human body. And in fact, sorry, this was a 10 centimeter square device, and a few milliwatts in an industrial setting with 10 to 20 Kelvin of temperature difference. Now, this is a bulk thermoelectric device. There have also been innovations in trying to micro-machine these PN legs in such a way that you can put many more of them in series. And what that helps you with is it tries to increase the Seebeck coefficient. So from the 23 millivolts, you now go up to 155 millivolts per Kelvin. What that primarily helps you is in the interface circuit. I mean, it's very hard to operate out of 20 to 50 millivolts of voltage coming out of the harvester. When you increase that voltage, it's easier to build circuits, and more efficient power management circuits can be built. But this is another commercially available harvester. The power levels are more or less similar. So in concept, you can think about a wearable kind of a system where you're applying a thermoelectric device. The temperature difference between the body and the ambient is going to provide the energy to power a system. And this is just an example of a similar system built, worn on the arm of a person. And the chip basically takes in the small amount of voltage delivered and lifts it up to a capacitor or supercapacitor from where you can power your radios and microcontrollers. And in this kind of situation, we were getting around 50 microwatts when worn on the arm. The other way to get energy is from ambient mechanical vibrations. Could be broken down into two broad categories. One is an electromagnetic wave, where mass attached to a coil is swinging in between a permanent magnetic field, and so you generate electrical energy thus. Or through piezoelectric means, which are smaller devices compared to the electromagnetic ones. The one shown on the left is actually a piezoelectric device. So when you apply mechanical strain on this device, now you're generating an electrical voltage, which can then be taken using the power management circuits to charge up a battery or a capacitor. So if you look at the typical power numbers here, I mean, you can have an electromagnetic device on your pocket or something, and when you're walking around, or in the sole of your shoe. But that's a very low amount of power because, firstly, the frequency is very low, and the amount of G's that you get, the acceleration that you get is also pretty low. But these are very good for industrial situations where you put it on a machine. One of the primary issues with mechanical vibration harvesters is these need to be very high Q systems to extract proper energy out, to properly couple onto the mechanical side. And so when you look at it, I mean, the bandwidth is usually 1 to 2 hertz. So in an industrial setting where a machine, I mean, you have 60 hertz vibrations or so, then it makes a lot more sense there, where you tack on this harvester onto the machine and you're getting a few milliwatts of power. Now you can just monitor the machine, see whether it's operating correctly, do fault diagnostics, and radio the data out. So these are pretty useful in that kind of a system. Another system I'm showing here using vibration to electric energy is, I mean, you can tack on some of these on a pipeline to monitor whether it's corroding or not. In the middle, what you see is a MEMS-based micro machine, the piezoelectric device, out of a research lab. And so it was able to generate around a few tens of microwatts for the accelerations available from the surroundings. And again, you'll have a dedicated power converter for this to take in that AC wave, rectify it, and charge up your battery. Finally, I'll briefly mention that you could also power up your systems without a battery using targeted radio energy, I mean wireless energy. The simplest of that would be regular inductive coupling. And there's a lot of products available in the market today. People are even powering up cell phones using pads, I mean, inductive coupling. And this is a well-known technology, I mean, except that it's not true self-powering in the sense you have to target energy from the transmitter. But here I've just showcased a device where you have a medical patch on your body, and then that patch is basically powered by a transmitter coil on your on the T-shirt or so. And so this can be powered. The patch is powered, and then it can wirelessly also transmit data back along on the same channel to the transmit side, which can then be connected to your cell phone or so. And so this is also possible. But if you want to truly decouple from the transmitter and go, I mean, increase the distance, it is also possible to power on the far field, but then the power drops off significantly, and it becomes kind of impractical after a certain distance. So those, in brief, we talked about the energy sources themselves. Typically, in indoor or wearable situations, we're talking about a few tens of microwatts. In an industrial or bright sunlight situation, we're talking about a few milliwatts of power per centimeter square or cube, depending on what the harvester is. And so this energy is now then taken out and then stored in a rechargeable battery or a supercapacitor before it can be powered to the load. So firstly, the question is, why do we need to even store it? Why can't we just power the load circuits directly from the harvester? I mean, you're just wasting efficiency, or I mean, you're just wasting power, sending it to the storage, and then taking power from there and powering the load. So the reason being, I mean, most of the systems that we're talking about are heavily duty cycled, firstly, to reduce the overall power consumption, to even make self-powering a viable alternative. So when you're duty cycling it, I mean, the curve on the red is basically, you can think about a sensor node waking up every so often, doing some local processing, and then radioing the data. And so the power consumption of the load is very, very intermittent. And on the green is where I'm showing is the average power available from a solar cell. So you can clearly see, I mean, you cannot just directly connect the solar cell to the radio. I mean, there'll be large periods of time where you cannot, I mean, when the radio needs power, you won't be able to get enough. And so the storage basically acts as a buffer, and it kind of mitigates the disturbances between the input power and the output power needed. And so it accumulates all the energy when it's available from the harvester, and then it provides it to the load when it demands it. And so it's essentially a smoothing function being done by the buffer. So the typical buffer, or the storage medium that you're looking for, the key characteristics would be how much energy can it store in a given form factor, whether it's able to provide enough power to the load when it demands it, and then it should have very low self-discharge because you don't want your storage medium to leak out all the energy that you obtained from the harvester. So that being the case, I mean, we will look at 3 different storage techniques, one being conventional rechargeable batteries. These have a lot of capacity, in the sense it can go up to a few amp hours of energy capacity, so in that way they're pretty dense. And they also have very low impedance when you're talking about a AA or AAA battery, that it can provide a few hundred milliamps of current needed by the radio when it wakes up. In the case of coin cells, though, they do have quite a bit of internal impedance, so we may not be able to power a 50 milliamp radio directly out of the coin cell. You need to buffer it some more with decoupling capacitors and stuff. The other problem with the conventional rechargeable batteries is their recharge cycles are quite limited. I mean, they lose capacity with increased recharge cycles. And the self-discharge, they do discharge quite a bit, too. The other more popular technology that's coming up recently is thin-film batteries that use solid-state electrolytes. So this is something like a lithium polyoxynitride electrolyte, which doesn't leak at all. So these can hold charge to within 1 or 2% of self-discharge over a period of a year. And they also, I mean, they've been engineered to provide currents of up to 30 to 40 milliamps. So these are good for a sensor node kind of application where your radio would need a peak power of around 30 to 40 milliamps. And being solid-state electrolyte, I mean, they have a lot of recharge cycles, and they can operate at high temperature environments. The capacity typically around 2 milliamp hours. But they're very thin in form factor, and so you can gang a lot of them in parallel too. And the third option would be supercapacitors. Now, I mean, these have, they're not chemically storing the energy, so they have a lot of recharge cycles. But the problem being that self-discharge is very, very high. The other key benefit of the supercapacitor is it can provide as much power as you want when the load demands it. So in that way, it's very beneficial. Capacity being quite low, too. Now, you don't have to only use one, I mean, it's not mutually exclusive. You could think of a system where you have a big thin-film battery and then a very small supercapacitor in parallel with it, which combines the benefits of both of these systems. So you can deliver as much power as you want when needed, while keeping the self-discharge to a minimum. So before we move on to the energy management circuits, this slide just simply shows what the duty cycle impact on the average current of your load circuit is. On the x-axis I plotted is the activity interval, the time between wake-up cycles, and the pulse width being the amount of time with the sensor's on, consuming the active current, and then it goes back to sleep, and after the activity interval, it wakes up and transmits again. And so if you just plot that, if you just assume an active current of 1 milliamp and sleep current of 1 microamp versus 0.3 milliamps and 0.3 microamps, the curve basically shows very soon you hit the knee of the curve, and then you're completely dominated by the sleep current of the system. Now, as I mentioned, in an energy harvesting situation, the sleep current, not only is the battery self-discharge need to be taken into account, but the overall energy management IC is constantly on, trying to extract as much energy from the harvester. So the quiescent current of your energy management IC becomes a critical parameter in self-powered systems. So with that said, let's look into what these circuits look like. So over the next few slides, I'm going to talk about what the inside of an energy management IC looks like, and I'll briefly touch upon the circuitry. So I'll talk about it with the help of a commercial energy management IC available in the market today. It's called the BQ25570. And it's designed to interface to energy harvesters, a wide variety of them, being solar, thermal, or piezoelectric, and then it can charge either a rechargeable battery or a supercapacitor. And it has the ability to provide a regulated output voltage to the load circuits. So on the interface side, it handles voltages from 100 millivolts all the way up to 4 volts. So you could interface either to wearable thermoelectric devices or multiple cells of solar cells in series too. Power levels, it can handle from a few microamps all the way up to 100 milliamps at the input, the current levels, I mean. And on the output side, it provides regulated voltage between 1.3 and 5 volts. And the battery can be anywhere from 2 to 5.5 volts. The IC also has battery management features, specifically for overvoltage, battery OK thresholds, and the output regulation settings. And all of this functionality is performed with just 480 nanoamps of quiescent current. So let's look at how does the charge itself look like. It's a very simple pulse frequency modulated voltage regulator. In this case, in the harvesting, the charger case, we're trying to regulate the input voltage. Typically, when you talk about a DC-DC converter, you're looking at regulating the output voltage to provide to your processor. So the charger itself is an input voltage regulated system. You want to regulate the input to the maximum power point of the harvester. And then you take that energy out, and every cycle, it dumps charge onto the storage node. And it's got some other digital logic functionality to do over voltage protection and the cycle-by-cycle comparison for the input voltage. The key thing here is there's no constantly on clock, so you want to minimize the quiescent current. You've got to bias these systems at a few nanoamps and remove all clocks that are in your system. And so that's what the charge itself does. And if you look at the efficiency, now the energy that you're taking out of your harvester, you want to efficiently transfer to the storage node. And so this system, if you look at from 10 microamps all the way to 100 milliamps, we're talking about around 80% or so efficiency. And then across the load voltages, it goes from 100 millivolts all the way up to 4 volts. For a typical solar cell, which provides around 0.5 volts, we're above 80% or so. So that's the typical kind of numbers that we're looking for when we're taking energy out of the harvester and putting it in the storage. Now, as I said, we did look at the solar cell MPP curves. Now, an interesting observation here is if you plot a constant fraction of the open circuit voltage of the cell, in this case, for this cell, it was around 73% of the open circuit voltage, you see it lines up very close to the maximum power point of this solar cell itself, in fact, to within 0.5%. So what this is used for is, I'll describe how the maximum power point tracking is done. So how do you know what you have to regulate your input voltage to? So typically, I mean, in bigger solar power, I mean, on your house installation and stuff, they do what is called slope tracking. Basically, they go along this curve from a lower voltage to a higher voltage. They measure the power obtained at each point, and then they're going to settle on the maximum power point. But for the kind of systems that we're talking about and the kind of quiescent currents that we want to achieve, it's just impractical to do any of these sophisticated algorithms. So we need to go for simplistic ways to do maximum power point tracking. So what's done here is basically, OK, we know that a constant fraction of your open circuit voltage is close enough to your maximum power point. So all the system does is every so often, every 16 seconds, it disables the charger. The input is going to ramp up to the open circuit voltage of the attached harvester. And then a fraction of that is sampled and held onto an internal capacitor within the IC. And that's used as the reference moving forward for the next 16 seconds. And that's what the charger is going to regulate the input to. So this way, we achieve open circuit sampling, maximum power point tracking, almost with no less than a few 10 nanoamps or so of current. Now, the good thing with this is it's not just for solar cells. If you apply it to thermoelectric harvesters, typically the maximum power points are at 50% of the open circuit voltage. And so this, methodology is then applicable to a variety of harvesters too. Here I'm just showing, how it's exactly done in operation. So on the green is, let's say, hypothetically, this is how your open circuit is moving on your solar cell. So periodically, every 16 seconds, you see that the charger is disabled, and that lets the input go up to the open circuit voltage, and then you sample and hold 80% of that. And that's what the yellow voltage is the input, and that's what it's regulated to for the next remainder of the 16 seconds. And this repeats. Let us now, if we look at cold start, in this IC, when you apply an input voltage of about anything about 330 millivolts, the IC can kickstart itself from the input, even when there's no energy available in the storage medium. So how it does that, this is just a cartoon. Basically, when the input light impinges on the solar cell and the input voltage ramps up enough, it crosses the 330 millivolt threshold, there's an internal POR circuit. It's a power on reset circuit that detects that, and then it keeps turning on and off the switch, and that just charges up the storage medium. And this process just keeps repeating as long as there's power available from the input, till the storage medium reaches a certain voltage. In our case, it was 1.8 volts. And once it reaches enough voltage from which you can run regular circuits off, then you bootstrap your system from the storage and run your circuits. Because this cold start is essentially not that efficient. You're just using it to kickstart your system from a completely dark state. And then once you have enough energy in the storage, you go on to your more efficient charger. We've talked about the charger and the cold start circuit and the MPPT block. Now let's look at what are the options available to take the energy from the storage medium and provide a regulated output voltage to your load circuit. This is common to both a self-powered system and a battery-operated system. There's mainly 3 different alternatives available. One is the typical linear regulator. It's a very simple circuit wherein, you're regulating the output voltage basically by modulating the resistance of the pass FET. And it could be very simple. It can provide scalable output voltages. It's very small in size, and you can put many of them, if needed, to deliver to different load circuits. Now, the fundamental problem being the current delivered to the load is the same as the current taken from the storage. And so your efficiency is typically not typically, but it is essentially limited to the output voltage divided by the input voltage. So if you're talking about a 4-volt battery and you're powering a processor running at 1.2 volts, you're not going to get anything more than 30% in efficiency. Now, to improve efficiency, you've got to go on to switching regulators. Here again, there are 2 main classifications. One, you do energy transfer using only capacitors. So that's a switch capacitor converter. It's very good in the sense you can integrate the capacitors on chip, so it can be a completely on-die solution. But you're limited in the amount of capacitance that you can put on chip, and that limits the amount of load current that can be delivered using this converter. Again, you can put multiple of these in parallel on the die and try to get different voltage domains. I'm just showing an example of a system that was built using an on-chip switch capacitor converter. It's a microcontroller. It was designed to operate near threshold, around 0.3 to 0.4 volts, therein significantly saving the amount of energy per operation needed. It in fact operates very close to what is called a minimum energy point. I think the next speaker is going to talk more about it in detail. But if you want to operate somewhere there, but your external circuit, external storage has a 1.2 volt or more in voltage, now you need a regulator to provide this low voltage, and it better be efficient, otherwise you're not getting all the benefits of your minimum energy operation. And so in this system, we just embedded a small DC-DC switch capacitor converter on it, and you can see the area of it is quite small compared to the memory and the logic itself. And it was quite efficient, providing around 75% efficiency down to a microwatt of power consumed by the memory and the logic. So that's just an example of how you can use a switch capacitor converter. So if you want to run the memory at a different voltage compared to the logic, you can just put on another DC-DC converter and you can go with it. Now the third alternative is the more efficient alternative. It uses an inductor, an off-chip inductor, to provide your regulation. And it can provide any output voltage as needed. It could be lower or higher than your storage, and it provides typically greater than 90% efficiency. And so in self-powered applications where the energy efficiency is quite critical, we typically tend to move towards the inductor-based switching regulators. One such example is a commercial IC available, which it's used to provide up to 50 milliamps of load current, and operates from an input from 2 to 5.5 volts, provides output voltage between 1.3 to 5.25. And the architecture is very similar to the charger that was described. It just operates in reverse. Instead of regulating the input, it regulates the output. And if you look at the typical efficiency number of such a converter, we're talking about close to 95% efficiency all the way up to 50 milliamps. And the beauty of it is, since it's completely digitally controlled with no running clocks, its quiescent current is only 360 nanoamps. So what that enables you to do is you keep reducing your load power, and the efficiency doesn't drop off. In fact, we can look at it all the way down to 2 microamps of output current. You're above 75% in efficiency, so that is significant. Most even linear regulators do not have quiescent currents this low. So now that we've looked at regulators too, I'll briefly touch upon what the essential battery management functionalities need to be, and how a self-powered system knows whether there's enough energy or not in the storage medium for it to get powered, the power good indicator. So the typical essential peripheral circuits that's needed within such a system, you have a very low power clock just to do energy management of the system. You got the state machine, which runs your maximum power point tracking clocks, which enables or disables your buck converter, the regulator, the charger, and then you've got your band gap, which is needed for regulation reasons. And the main thing is the battery manager, which does the under voltage, over voltage, and the temperature protection of the system. So typically, when you think about it, regulation is usually done by having a resistive divider from your load or output voltage and then comparing it with your band gap and saying, okay, whether I'm higher or lower than that, and that's how you do over voltage or under voltage detections. Now, if you think about it, if your battery is sitting at 4 volts and your resistor string is even, say, 10 mega ohms, you're already consuming 400 nanoamps of current just in that resistor string. So how do you expect a system to have 480 nanoamps of quiescent current? So we need to think about techniques to reduce the power consumption here. And so in these low power systems, the battery is not moving very fast. So this system basically takes advantage of that and says, okay, I'm just going to look at the under voltage and the battery OK thresholds for a small amount of time every 64 milliseconds, and that should be good enough because the storage is not moving very fast. We're just charging it with a few tens of microamps of current. And essentially, that's what this does. It connects the storage voltage to the resistor divider. It's, if you want to think about it, it's duty cycling at a lower scale. You're duty cycling even the battery management in your system. And that's how we're able to reduce the power consumption quite a bit. So if you look at the typical current breakdown of the overall energy management IC, the band gap is duty cycled within the system, and so overall it only consumes 85 nanoamps or so. The buck converter and the bias current blocks consume a few, around 140 nanoamps. And you can see overall everything is optimized critically to keep the overall quiescent current of the system down. And once we reach the under voltage threshold, the system has an inbuilt switch which decouples the storage from everything else, and you go to less than a nanoamp of leakage. So this just shows how such a system starts up. As I said, initially there is no voltage anywhere in your subsystem, so the storage and the battery are at 0. The input is applied, say the solar cell lights up, and then you have about 330 millivolts at the input, and the storage slowly keeps coming up. It gets charged through the cold start. And then once the storage voltage reaches somewhere around 1.8 volts, that's when the system bootstraps and goes into the regular charger mode. And before it goes into the regular charger, it tries to do open circuit MPPT sampling so that it knows how much it should regulate the input to. It continues regulating it while the battery and the storage now charge up at a much faster rate because the charger is more efficient. So you can see the inflection point in the charging waveform. Once the storage reaches the under voltage threshold of the battery, that's when the battery the switch is connected so the battery can power the overall system. When we reach a threshold which can be externally set called the battery OK, this tells the load circuits, okay, now there's enough power for you to power the system. And so that's what the battery OK threshold is for. And then once we reach the over voltage threshold of the battery, the entire system just shuts down. There's no more energy obtained from the input. So that's the energy management IC. How are we going to use it in a typical system? Here I'm showing some research work that was done out of MIT, which shows a computing architecture that can be used with energy harvesting. The IC itself uses memory cells which are non-volatile, using FRAMs, in the sense they can be turned on and off. You can come out of sleep and active state instantaneously. So when the energy harvester is powering this kind of a system, and when there's enough energy available, the battery OK signal is high, and the processor is running properly. And say once the energy is there's not enough power available from the solar cell or the harvester, the voltage on the storage is going to drop, and the system recognizes that the VBAT OK threshold goes down. It stores the existing state of the system in this non-volatile memory and immediately goes to sleep. And then once there's enough voltage available on your storage and the VBAT OK threshold goes up, it instantly comes back from the sleep to active state and resumes operation. So this kind of paradigm is very essential when we're talking about intermittent power availability from harvesting systems. Now, there may be very critical systems where you cannot afford to lose power at all. And so in those situations, you can also think about energy harvesting using a battery backup. Now, the beauty of this is there are ICs available which would autonomously figure out whether there's enough power coming in from your harvester side and move the powertrain to the harvested energy. And in cases where there's not enough power, then you use the regular primary battery to power the load. The good thing being now you don't have to design your harvesting system for the complete Six Sigma case of not having power for a long, long time. That would essentially mean you need to size up your solar cell or a storage to really impractical levels. Now, with this kind of system, you can think about doing a 1 or 2 sigma design, meaning a primary battery can be very small and your secondary storage can be small, and you obtain the benefits of both worlds without using too much of capacity from your primary. We could also think about combining power from a variety of harvesters and providing different load circuits using a single off-chip inductor. And so there are solutions available to do energy combining from a variety of harvesters while keeping the overall solution size to a minimum. And we can also provide different load circuits using, you can run multiple regulators out of the same inductor using the concept of inductor time sharing. Finally, before I conclude, I'll just show you an example of a solar-powered Bluetooth LE beacon system. The table, okay, it's not clearly visible, but basically it's got the energy, the power breakdown of the different BLE modes and how long it's active. There's also an LED in the system which blinks periodically. And so the overall power consumed by that system is around 180 microwatts if the Bluetooth beacon is sent every second. And the solar cell itself can provide around 400 microwatts for the size available at 450 lux. And so the system is essentially very simple. You've got the solar cell, you put in an 8 millifarad supercapacitor, and you've got the energy management IC in between. And the IC just has a load switch to the Bluetooth LE, the radio. And so this is a reference design that's commercially available. You can take a look at it, and it's fairly simple in the sense you can just put it in an indoor light situation, and it's going to keep transmitting data. And so you can tack it onto a sensor, too, and it can measure either the temperature or occupancy. So in conclusion, the advances in circuit design techniques and architectures have dramatically reduced the power consumption of circuit blocks to such an extent that now it's possible to think about self-powering these systems. But when you come to self-powering, the characteristics of the energy harvesting sources and storage medium differ quite a bit from regular battery-operated electronics. And so you need to think about specialized interface circuits and optimize energy processing elements to manage the ultra-low power levels output by these harvesters. And in the end, a holistic optimization, not just of the harvester itself, but of the complete energy management system, it's needed to build a viable and practical IoT node or subsystem. So thank you very much. Okay.
Okay, next speaker is Massimo Alioto. He is a professor, an associate professor at National University of Singapore Electrical Engineering Department. He's also associate editor-in-chief of IEEE Transaction on VLSI System. His research interests are low-power VLSI circuits, self-powered and wireless nodes, and near-threshold systems. So he has been visiting scholars in multiple organizations such as Intel Labs, UC Berkeley, University of Michigan, and EPFL. He has a master and PhD in electrical engineering from University of Catania, Italy. So he's going to be talking about low-power approaches for designing IoT devices. Massimo?
Yes, thank you very much for your kind introduction. And good afternoon, everybody. So I'm truly really excited about being here. I'm a bit jet-lagged, I have to say, but I'm super excited by the fact that we'll be talking about IoT, Internet of Things. So it has come the time to talk about these potentially very impactful technologies for the next 5–10 years. So in this presentation, I will basically talk about ultra-low power design approaches, which means essentially ultra-low voltage for IoT. And my presentation will be structured as follows. First, we will talk about the context, so what is truly specific to IoT designs. Then we will talk about ultra-low voltage operation, the necessity for it. And then we will talk about the challenges, design challenges that ultra-low voltage operation poses, as well as promising solutions to these problems. And this will be about three main challenges, basically performance, leakage, and resiliency degradation at ultra-low voltage. And then I will wrap up. So let's get started with the context. We have to say that the peculiarities of IoT nodes are defined by the intersection of different features that are basically set by physical constraints, such as size or power delivery, as well as capabilities, such as computing, processing, and communication, as well as the interaction, the way IoT nodes interact with the external world. Regarding the size, usually the size of the system is mainly defined by the energy source, the battery or the energy scavenger. And we might say that usually, hopefully, the size of IoT nodes should be from a few cubic millimeters to several tens, let's say 100 cubic millimeters. Then, of course, any IoT node needs to be self-powered because it's untethered. So this means that the power budget available is actually very small. Just to give you a few numbers, if we are using a purely energy-scavenged system, we have typically microwatts, maybe a few tens of microwatts. And if we have a purely battery-operated system, we have even much less, in the order of tens of nanowatts, maybe 100, if you want to operate off of a button cell battery, for example, for 10 years. But if we can actually afford recharging the battery regularly, for example, every week, and this could be, for example, the case of wearable electronics, maybe we might have something in the order of tens of microwatts. The fact that we have IoT nodes that are continuously available, so always connected, doesn't mean that we can perform useful operation all the time, because this would be impossible with such a short, tight power budget. So what we have to do is, occasionally, we do some active task in active mode, but most of the times, actually, we operate in sleep mode. Regarding the computational ability of IoT nodes, we should observe that such nodes usually perform repetitive tasks. So we can actually leverage, in this case, specialized hardware to basically perform these tasks well and with high energy efficiency. And regarding the communication, which clearly has to be wireless, well, it's pretty energy hungry, but we can reduce it by putting more intelligence in the IoT node so that the node has to communicate only when strictly necessary. So Now I would like to clarify the role of power and energy in IoT nodes. Well, I will resort to the duty cycle scheme that I was mentioning before, this one. So most of the times, sleep mode. Sometimes we go into active mode. So this simple scheme actually suggests a very general architecture of IoT nodes, which is a little block always on. So even in sleep mode, this node, this block is running continuously. And this block is meant to basically retain previous information or trigger the next event. And then the rest of the circuit, of the system, so the large part of it, is actually duty cycled, so it's activated only in active mode. Well, this means that we can actually write the power of the IoT node as the sum of two main components. One is the always-on power, it's constant, and one is the duty cycle power, which is basically the active energy spent during the task that we perform regularly divided by the wake-up cycle. So if we look at this equation, actually, we can learn something interesting. Basically, minimizing power is something that matters for always-on blocks, because we want to minimize this and that. So power matters for always-on blocks, whereas energy matters for duty cycle blocks. So that's why I'm saying that we should minimize power for always-on block and energy for duty cycle. Well, if we want to minimize power, we should consider that usually, actually always, we have, this is the case. Basically, the power is monotonic, which means that if we reduce the voltage, we also reduce the power. So minimum power operation for duty cycle, for always-on blocks is equivalent to ultra-low voltage operation. So ultra-low voltage operation is absolutely necessary for always-on blocks. What about duty cycle blocks? Well, we want to operate at near the minimum energy point, right? And we will justify the existence of this minimum energy point, this one, in a couple of slides. So this minimum energy point usually is set to pretty low voltages. So once again, even for duty cycle blocks, actually, we need absolutely ultra-low voltage operation. So ultra-low voltage operation is absolutely key for any block in any IoT system. So ultra-low voltage operation, well, let's talk about it. So essentially, we want to operate at ultra-low voltage because we want to take advantage of, hopefully, a quadratic benefit when we reduce the voltage. But this comes at the cost of degraded performance. So the question is, how aggressively should we really scale down the voltage? Well, to understand this aspect, we should look at the qualitative plot of performance, this green curve, versus VDD, and energy, this blue curve, versus VDD. So if we look at performance, basically, when we operate in above threshold, so this is the transistor threshold, this one. So if we operate above threshold, we have basically roughly a linear performance degradation when we reduce the voltage. Instead, if we operate at voltages that are below the threshold, so here, the red area, actually the performance is degraded severely, basically exponentially, as I will show in a couple of slides. And if we look at energy, we have a quadratic benefit at above threshold, and we reach a minimum energy point, which is close to the threshold voltage of the transistor, and then actually the energy goes back up for reasons that we will understand in a couple of slides as well. So from this picture, actually, we understand that if we operate close to the threshold voltage, so near threshold, this green area, this is kind of a sweet spot, because in a way, regarding the performance is degraded compared to full voltage, nominal voltage, but not too much compared to subthreshold. And also, energy is close to the minimum possible value. So we will try to operate at near threshold. Every time we will want to preserve decent performance, and we want to also minimize the energy. So duty cycle blocks. Instead, in subthreshold, we basically have low speed, very low speed here. And energy might not be even minimum if we push aggressively on the voltage, but we certainly can have minimum power. So that's the right spot for always-on blocks. Okay, here in this slide, I'm showing just an example. This is the first cubic millimeter system. It was published at ISSCC 3 years ago by UMich, University of Michigan. And here you can see energy versus voltage and throughput versus voltage. And their trend is basically the same as what I showed in the previous slide. If we want to give a more rigorous definition of near-threshold operation and sub-threshold operation, we should actually refer to the region of operation of transistors. So we will say that we are operating in near-threshold if transistors are working in moderate inversion, which occurs for typical and recent technologies for supply voltages in the order of 400 to 600 millivolts. Instead, we will operate in subthreshold if the transistors are working in weak inversion, which happens when the supply voltage is, let's say, below 400 millivolts. And by the way, these numbers will not change much in the foreseeable future because the ITRS roadmap predicts that down the road, throughout the development of next technology generations, actually, the supply voltage and the threshold voltage will not change much over time. Since we were talking about performance, well, performance is basically dictated by the on current of the transistor. Okay, so let's talk about a simple and very popular model of the transistor. It's the EKV model, and it's trans-regional because it's a single equation that holds in any region: weak inversion, moderate inversion, strong inversion. In particular, this model expresses the current, or more precisely, the inversion coefficient, which is basically the on current normalized to a process-dependent current. But it's essentially the current, right? As a function of V, which is basically the gate over drive, VDD minus VTH, divided by something else. But it's essentially the gate over drive. So this is the IV characteristics of the transistor. And by convention, we'll say that we'll operate in near threshold, so moderate inversion, if the inversion coefficient ranges from 0.1 to 10, and we will say that we are working in subthreshold when the inversion coefficient is lower than 0.1. Okay, we can now approximate this equation into the 3 different regions that we have mentioned, and while doing this simple exercise, we can see that in weak inversion or subthreshold, the IV characteristics is basically exponential. And this is why in subthreshold, the performance is degraded very significantly, exponentially, when reducing the voltage. Then, in moderate inversion or near threshold, we have basically quadratic behavior. And then, in strong inversion, we have an almost linear behavior. So from these 3 equations, we learn something, which is the curve of ion versus VDD is actually pretty steep. It's super linear in near threshold and subthreshold region, which means that, first, performance is pretty sensitive to both the supply voltage and the threshold voltage in both near threshold and subthreshold. Second, the choice of the threshold voltage is actually pretty important, pretty critical in terms of performance. We will talk about that later. And also, unfortunately, the sensitivity of the performance to VDD and VTH threshold voltage variations is actually pretty high, which actually raises concerns about robustness. If we want to talk about performance in a more direct way, we can refer to the well-known fan-out for delay, which is a good metrics for both the speed of technology, so process engineers use these metrics very frequently, and as well as microarchitects, which, since usually the clock cycle is expressed as a multiple of f(4) through a multiplying factor, which is called effective logic depth, which is basically the effective number of logic gates between subsequent registers. Okay, let's have a look at this plot in 28 nanometers. So this is the normalized f(4) delay. As we can see here, in near threshold, f(4) is basically 10x worse than at nominal voltage. So this means that we are losing an order of magnitude in terms of performance when operating at near threshold. And if we operate in sub-threshold, we lose more, 2, 3, 4 orders of magnitude. Very, very slow. So we have also some good news, which is, for example, VDD can be actually used as a very, very powerful knob to dynamically improve performance when needed. For example, let's assume that we boost the voltage, the supply voltage, by 100 millivolts. So we are temporarily raising the supply voltage by 100 millivolts. If we do that in sub-threshold, typically for typical technologies, we get something like 7, 8x better performance every 100 millivolts boosting. In near threshold, we will get something less, but still significant, from 2 to 4x. So from these numbers, we learn something. In sub-threshold, voltage boosting is very effective in raising up the performance, but it's not that useful, because in the end, performance is already pretty bad. Regarding near threshold, actually, voltage boosting is much more interesting, because we can get decent performance, we can raise it significantly by 2, 4x, and by the way, the energy cost of voltage boosting is not much, because if we are operating at 500 millivolts and we raise it by 100 millivolts, we are increasing the energy by, if we assume a square law, by still a pretty limited amount. So this suggests the idea that actually selective voltage boosting can improve significantly both area efficiency and energy efficiency. What I mean by selective voltage boosting is that we raise occasionally and with fine granularity the supply voltage of small portions of the circuit. Let me show an example that can be pretty representative. Let us assume that we have a large transistor with large strength, which is driving a large network, could be a digital module, with lots of transistors, but small. This could be, for example, a sleep transistor or a buffer. Well, in this case, let us assume that we are working at a nominal voltage of 500 millivolts. Then, if we increase the voltage, the gate voltage of this transistor from VDD to VDD plus delta VDD, with delta VDD in the order of 100 millivolts, 200 millivolts, and so on, well, what we get is that actually the strength is increased superlinearly, as we noticed before. So it means that at iso strength, I can actually raise the voltage a little bit and reduce superlinearly the size of the transistor. This justifies why the area of this transistor is actually decreasing pretty fast. So we are improving the area efficiency quite a bit through voltage boosting. And in the end, if we push on the voltage boosting as much as possible, as much as allowed by the technology, we can get basically an order of magnitude reduction in area of this transistor, which is pretty remarkable. If we look at energy, we have a similar effect, because in the end, the energy that we have to spend to turn this transistor on is C, where C is the gate capacitance of this transistor, V squared. So in this case, since we are maintaining the same strength, C is being reduced superlinearly, right, if we apply some voltage boosting. And V squared is not really increasing much if we are applying some kind of moderate voltage boosting, I don't know, 100 or 200 millivolts. So in the end, we can improve the energy efficiency, so reduce the energy to drive this transistor by a factor of 2, which is still pretty interesting, right? And of course, we have beyond a certain point, we actually have the energy going up again just because the quadratic energy cost is just increasing, because we are applying a significant voltage, amount of voltage boosting. So now that we have introduced ultra-low voltage operation and the basic features, let us talk about the fundamental challenges that ultra-low voltage poses. One is performance degradation. Actually, I would like to say that it's not necessarily an issue, because IoT nodes usually don't really require very high performance. So typically, we might say that we might need from a throughput of mega ops per second, hundreds of mega ops per second, down to kilo ops per second. Depends on the application, of course. And this range of performance is fully compatible with the range of performance that we can get in near threshold down to sub-threshold. So actually, the performance degradation at ultra-low voltage might not be an issue in the IoT case. Also, we should observe that the wire delay in IoT nodes is not a real issue, because the gate delay is certainly dominant, because we are working at ultra-low voltages. So FO4 in the gate delay tends actually to be much higher than the wire delay. So it's gate dominated. What if we need some performance, some significant performance from time to time? Well, we can still boost the voltage up to the full nominal voltage, right? So for example, we can assume that we want to go from 400 millivolts to 1.2 volts here. And what we get, if we do that, is basically a 10x improvement in performance. But the energy per operation is increased basically quadratically, so about 10x as well. But this is not an issue if we do this only infrequently. Also, we should observe that if we design the system for the common case, as we should do, we should optimize it for near threshold operation. So when we operate at 1.2 volts, actually, the energy efficiency will be degraded compared to a system that is specifically designed for just 1.2 volts. And this energy efficiency degradation is typically in the order of 20–25%, as was pointed out in this paper by Intel, published 2 years ago at ISSCC. Well, there are other tricks that we can play to improve performance at the expense of a bigger area, which is parallelism, which is certainly not a new concept. We have been looking at multi-core processing for a decade now. Another trick that we can play is actually specialized hardware. So using specialized blocks that perform certain repetitive tasks well and in a very efficient way. What about energy efficiency? Well, the energy of an IoT node is typically the sum of two contributions. One is dynamic energy that can be reduced quadratically when we reduce the voltage. And the second is leakage energy that can be written as the product of voltage, leakage current, and then the clock cycle, which can be written as FO4 times the effective logic depth, times the number of cycles required for each operation. Okay, the latter two parameters are set basically the microarchitecture and the architecture. So these are numbers for us when we reduce the voltage. Then when we reduce the voltage, this is reduced linearly. This is reduced somewhat superlinearly due to the Dibble effect. But FO4 at ultra-low voltages actually tends to be increased significantly. It goes up very rapidly when the voltage approaches the threshold voltage of the transistor. That's why we typically observe a dramatic increase in the leakage energy here at low voltages. So we are learning that the leakage energy actually tends to increase significantly at low voltages. Okay, let's put everything together. So we have dynamic energy here, leakage energy here. So the overall energy has this green trend. So we have a minimum energy point, interesting, which is typically pretty flat, and it can also lie either in near threshold or sub-threshold. This is a picture that I took from the Intel paper that I was mentioning before, and it depicts basically the energy breakdown. So when we work at nominal voltage, the leakage energy is 14% of the overall budget. That's pretty normal. That's what we would expect. Then, at near threshold, leakage energy is 42% of the overall energy budget. And if we go to subthreshold, it's even worse. It's 95%. So leakage energy is a big, big issue at ultra low voltage. We might think that we have a full bag of tricks, of traditional techniques to reduce leakage, the tricks that we have developed in high-performance systems, right? No, wrong. That's because, actually, most of the techniques that we know of are actually pretty ineffective when applied at ultra-low voltage. For example, if we consider transistor stacking, this is pretty ineffective in practical cases because, basically, the effect of stacking is reducing leakage significantly, at least at nominal voltage. So at nominal voltage, and this curve refers to 2, 3, 4 transistors, basically the leakage compared to the single transistor is reduced by a factor of 10 or even more, so by a few tens, by a lot. At the same time, the ion current for 2, 3, 4 transistors is not reduced as much. It's reduced by a factor of 2, 3, less than 4. So in this case, stacking is very effective because it's reducing leakage significantly, but it's not reducing ion, so it's not degrading performance significantly. What about near threshold? Well, as you can see, actually, the reduction in the off current here tends to be pretty close to the reduction in the on current. So in this case, it means that transistor stacking is not being very effective. And if we go to the red part, which is subthreshold, actually, transistor stacking is not effective at all because the reduction in off and on current are exactly the same. Well, what about power gating? We are used to introduce power gating all the time. Well, so let's consider the classical case where we have a sleep transistor that basically delivers a lot of current, ion, during active operation, active mode, and when we want to save leakage and we want to disable this block, we actually turn it off. So it delivers a current I off. So in this plot, at nominal voltage, we see that we have a large I-on over I-off ratio for the single transistor. This is good because it means that in active mode, we can deliver a large current, I-on, and in sleep mode, we can deliver a very small current, I-off. So the fact that I-on over I-off is large means that we can do that. Power gating is effective. But if you look at this curve, which is the I-on over I-off ratio, at near threshold, it's degraded by orders of magnitude, and in subthreshold, even more. So this means that power gating is not really very effective at ultra-low voltages. Well, we can use multi-VT. We can mix and match different VTs. For example, here in this figure, low VT and high VT cells. Well, let's present a simple example. So at 0.6 volts, for example, we have this green critical path, which is mostly low VT, as we might expect. And then if we reduce the voltage down to 0.4 volts, because we do dynamic voltage scaling, actually the critical path is changing. And this is changing because basically the delay at low voltages is dominated by HVT, high VT cells, because their delay tends to explode when the voltage approaches their threshold voltage. So if we look at the expression of leakage energy, we are actually degrading the leakage energy. We are increasing the leakage energy for two reasons compared to a single VT design. First, compared to a single high VT design, leakage is much higher in a multi-VT design. Why? Because we still have a significant number of low VT cells that have much higher leakage. And what about the clock cycle? Well, the clock cycle is actually increased significantly compared to the single low VT design because the delay, so the clock cycle is dominated by HVT cells. So in a way, we are paying for a doubled energy penalty. So this means that multi-VT is not really a good idea at ultra-low voltages. So how to counteract leakage? at ultra voltages? Well, there are various techniques. One might be fine-grained power gating. So instead of having one microprocessor core that is power gated by a single large sleep transistor, we actually split this microprocessor into small power domains, and each is actually power gated by a smaller sleep transistor. This means that we have more opportunities to shut down transistors, right? To save leakage. Well, but in this case, we have a problem because we have more overhead. Because in the end, we need certainly more sleep transistors, although smaller. We also need certainly isolation circuits at the boundary of each domain, as well as control circuitry to turn transistors on and off. We might use also fine-grained voltage domains, which means that we partition the microprocessor into small voltage domains, and we try to apply to each of those the minimum, very minimum voltage that still meets the deadline for the intended task. So in this way, we are also reducing their leakage energy. But once again, we have problems in terms of overhead when we divide the processor into small domains. We can also play with the market architecture, because in the end, the leakage energy is proportional to the effective logic depth. So this suggests the idea that we should actually break the circuit into deep pipelines. So many registers and very little logic between subsequent registers. And this was done, for example, 3 years ago by Yogesh in a paper published at ISSCC, where they showed that using a pretty aggressive logic depth of 17F04, they basically reduced the energy by 4x compared to the state of the art. And we still can play with the threshold voltage, which has to be chosen to the minimum value that meets the performance requirement, but it doesn't have to be lower than that, because otherwise leakage energy starts increasing significantly. And we can also use body biasing, at least for the technologies that have a decent dependency of the threshold voltage on the body bias voltage, such as FD-SOI, certainly not bulk FinFET. Because in this case, using body biasing in ultra-low voltages, at ultra-low voltages, makes perfect sense, because if we tune the body bias voltage, we are changing the threshold voltage. That has a significant, strong impact on performance and leakage energy at ultra-low voltage, as discussed before. Okay, now let us talk about variability and resiliency. Should we be worried about variations? Of course, because if we have delay variations due to process, voltage, and temperature variations, basically this design uncertainty forces us, designers, to increase the cycle time from the nominal one to a larger one, because we have to account for different sources of uncertainty: process, voltage, temperature, and even aging, right? So we have to care about variations. Let's get started with process variations. Here, we have, unfortunately, two negative concurrent effects when operating at low voltage. First, we have a large variability of the gate delay, sigma over mu. This is shown clearly in this picture, taken from an MIT paper, where basically the spread at 0.5 volts of the delay is much wider than that at 1 volt. And second, since the probability distribution function of the gate delay at ultra-low voltages is not Gaussian, it's actually close to log normal, this means that the gate delay distribution has a long tail to the right, which means that for a given level of confidence, we need a larger number of sigmas compared to Gaussian distribution, so nominal voltage. Just to get familiar with typical numbers, if we compare above threshold and subthreshold, and we consider the linear and exponential dependence of the on current, which means essentially performance, and the threshold voltage variations, if we do the math with reasonable values, we typically get 6, 7, 8% of variability in ion, and similarly on the gate delay at above threshold, so nominal voltage. But in subthreshold, if we do the math, we actually get much wider variability, 20x, much, much worse. And if we look at near threshold, we get something in the intermediate, typically 4, 5x. And also, if we want to look at the second phenomenon, which is the larger number of sigmas, if we consider the case of a Gaussian distribution above threshold, of 1 sigma, 2 sigma, 3 sigmas, if we consider a log normal distribution, so subthreshold, we need actually E sigma, E squared sigma, E cubed sigma. So that's a lot. So combining the two phenomena, it's evident that at ultra-low voltages, the variability due to process variations is huge and has to be managed in some way. And of course, at the system level, we can actually reduce the impact of variations by exploiting the well-known averaging effect. For example, if we consider cascaded gates, if we have many cascaded gates, actually variations are averaged out across these logic gates. So if we increase the logic depth, the number of cascaded gates, we reduce the path delay variations. But we are making the system slower. So the clock cycle is increasing, which means that leakage energy goes up. So that's a problem at ultra-low voltage. Improving the variability means that we have to degrade the leakage energy. And this is a very general fact in ultra-low voltage systems. For example, let us think about a different scale. So let us apply the averaging effect within a single standard cell. So we have a certain number of stacked transistors, and to reduce the variability, we would like to have several stacked transistors. But unfortunately, this means that the delay will grow, so the clock cycle will grow, which means that leakage energy will go up. So once again, variability and leakage energy are highly conflicting requirements. Well, let's go to the very basic level, which is a single transistor, and let's play with its own strength. So if we increase the strength, it means that we have less variability because we are averaging out variations in a larger channel area, but leakage is increasing. So once again, these two are highly conflicting requirements. That's a fundamental trade-off that we need to consider at ultra-low voltages. And voltage and temperature variations add further clock cycle margin. Typically, at near threshold and subthreshold, voltage variations determine an additional 30 to 50% margin, and temperature up to 100%. So that's a lot. So it means that we absolutely need to reduce or even eliminate such huge clock cycle margin. How to do that? Well, basically we need to compensate variations with some knob, which might be, for example, the supply voltage or delays in some way. And we can do that at different times. So if we do that at the testing time, we can certainly get rid of process variations because these don't change over time. But we still have to consider aging and temperature and voltage variations. If we, for example, do this kind of compensation at runtime, well, in this case, we can get rid of almost all the sources of uncertainty. So process variations, aging, and slow voltage and temperature variations. We can't really get rid of the fast ones, so their dynamics is comparable to the clock cycle, just because the system needs some time to react to these variations. So, of course, very fast variations can't be really tracked and corrected. Okay, so in the end, what we need to do to compensate variations is to compress this clock cycle until the point where we start seeing violations, timing violations, and then we back up a little bit. So this means that if we want to correct at runtime variations, and so eliminate completely the design margin, we need to detect timing violations. And there are several techniques to do that. One is based on in situ monitoring. So we have timing sensors that check if the transitions of the critical signals are occurring too close to the next clock edge. Or we can use some sort of prediction through tunable replica circuits that mimic the critical path. Once we detect errors, we can correct at several levels of abstraction, from software level to circuit level, right? So if we move to circuit level, we can have faster correction, but it costs more in terms of hardware resources because the correction circuit has to be implemented on chip. Well, we can even go more extreme by adopting negative margining. So instead of using a positive margin or a zero margin, as discussed before, we can even use a negative margin, which means we are using a clock cycle that is even smaller than the minimum clock cycle that avoids timing violations. In this case, of course, we have errors, and that's why this is called approximate computing. But in several actually applications, that is fine, as long as these errors are within bounds. For example, multimedia. If we are watching a video in our cell phone, if some pixels are a bit off, it's not a big deal in practical cases. If you're curious, you can check out this paper that we published this year at ISSCC in collaboration with University of Michigan, where basically we demonstrated the first SRAM with dynamically adjustable energy quality trade-off. Well, we should also say that when we operate at ultra-low voltages, actually, not only we have large variations in performance and energy, we also experience functional failures. So some of the circuits might not switch correctly. So that's why we typically introduce VDD min or Vmin as the minimum voltage below which some circuit starts not switching correctly. And if you look at the breakdown of the VDD min of typical circuits, this is mostly due to variations. And VDD min is typically for systems of moderate complexity like IoT. We don't expect to have billions of transistors in an IoT node, of course. Yeah, VDD min is in the order of 350 millivolts or a little more. But if we consider instead SRAM arrays instead of logic, this VDD min is much higher. And that's why SRAMs with low VDD min is a very active research area these days. Well, what to do about these variations? What we can do is, for example, using, and I'm referring to an idea that was proposed by University of Tokyo a few years ago. We can, for example, partition the whole system into small voltage domains and assign to each domain high VDD or low VDD to compensate variations. And these two voltages are actually very close to each other, tens of millivolts. So that's enough to compensate variations, but that's small enough that actually we can get rid of level shifters. So it means that we can partition this with very, very low overhead. Also, we can mention panoptic dynamic voltage scaling, where each block, ABC, is powered with one of the available voltages, and each block is powered every time by tracking the workload at the very minimum voltage that still permits to meet the performance requirement. Another idea that was published this year at ISSCC by Intel is the selective boosting. If we have a system where we have a little block, it could be the register file, for example, in a microprocessor, that has a higher VDD min and the rest has a lower VDD min, we can raise the voltage of this little block, register file, and then the rest of the system actually works at a much lower VDD. So effectively, it's a way to reduce the VDD min of the system. And we can do even cherry picking. So instead of being victims of variations, we actually exploit them. This is an idea that was proposed last year by UC Berkeley. So if we have a multi-core or many-core system, instead of just turning on and off cores, based on measurements, on chip measurements, we select the most efficient ones, which means that instead of taking any core by chance, we take the best. So we are actually exploiting variations to improve energy efficiency at low performance targets. So wrapping up, basically, IoT actually is not something unexpected. It actually follows a natural trend. And this trend, by the way, is not Moore's law. It's mostly about size and energy. So that's why I'm referring here to the Bell's law, this one, that says that every 10 years, typically, we reduce the size of computers by a factor of about 10 or more. Well, we are currently here, mobile, right? So next step is just IoT. And if we look at energy, so the Kumi's law, which is pretty recent, basically it says that every 1.5 years, we improve, at least historically, we have improved the energy efficiency by 2x, which means 75x in 10 years. Well, voltage scaling, technology scaling permits a 4x every 10 years. So the rest of it has to come from innovation. So for IoT nodes, we need lots of innovation. So wrapping up, we have shown that ultra-low voltage operation is absolutely essential in IoT nodes. We also showed that ultra-low voltage operation entails different design challenges, performance, leakage, and resiliency. And these challenges can be addressed through fine-grained schemes, across-boundary design, as well as adaptation. So just as a takeaway, if you have to take something home from this presentation, just forget everything, except in this figure. Because in the end, IoT node design is about three things. One is fine-grained tuning, which means trying to tune with very little overhead. Second, a cross-boundary design, which means thinking outside the box. And third, it's about adaptivity, which means context awareness. So this is the end of my presentation. Thank you for your attention, and I will be glad to take your questions on this presentation. Thank you.
Okay, thanks a lot. We're going to have a short break, and we start the next part of the tutorial at 4. Okay, everyone, we want to go ahead and get started with the second part, networking or connectivity for IoT. So we have two speakers talking about physical layer and home connectivity and IP standards for IoT. So let me introduce the first speaker. Mike Stauffer is Senior Director of Business Development at Qualcomm and at Tharus Technologies. He also had positions in several startups such as iBlast, Gain Micro-Optics, and Digital Video Systems. He has a bachelor degree from MIT and a master's degree from Stanford. Please welcome the speaker.
Thanks, Behnam. So, as Behnam mentioned, I'm with Qualcomm and Tharus. We're the part of Qualcomm that focuses on connectivity primarily in the home, things like Wi-Fi and Bluetooth and those sorts of things. So I'm going to be focused on that sort of area. If I can get this going, here we go. Okay, so first of all, I just want to sort of set the stage and the context for what do we mean by the Internet of Things, or the Internet of Everything, as we call it. You know, both terms are used in the industry. We like the Internet of Everything. And then I'm going to talk about specifically the IOE as it applies to the connected home. And then we'll talk about some of the details of the technologies that are used there. So the Internet of Everything is here. It's a big market starting to happen. Numbers that you see range from 25 billion that we like to use up to 50 billion, up to even 100 billion things being connected over the next few years. So whatever number you pick, it's a large number, and it's a big opportunity, and there's a lot of focus in the industry on it. It does have some implications for building out infrastructure as well to support all the bandwidth that's going to be required. So to constrain things a little bit, because IOE is very broad, covers a lot of things. You know, it covers sensors in the home. It covers sensors in the street. You know, street lights. It covers things in automobiles, et cetera. So we kind of think of things as a set of constrained ecosystems. Where the devices within those ecosystems kind of play together. So you can break this down a lot of ways. I kind of look at it as these four: smart home, smart car, smart body or wearables, and smart cities. And so we have focus in all of these areas, but our particular focus is really on the smart home piece. And so that's going to be the focus of where I speak to today. So let's talk about this connected home ecosystem. So when you have these IoE devices you're going to bring in the home, they have to operate in the environment of typically home networks that are already there. These are usually Wi-Fi networks, some cases power line plus Wi-Fi networks. And so we see this being built out as a network centered around a home gateway device. It might be what you have today is your access point or router. You might have a carrier gateway, something like that. Today they're pretty straightforward, pretty simple, but they're evolving very quickly to basically be pretty massive computers. You'll start seeing these smart gateways having multi-core processors, network processing, lots of memory. You can run applications on them, and they can basically really control your home network. And you can provide, you can write apps on them, provide services on them. They're going to be a key part of this home network. So the devices that are going to come into the home need to cooperate and utilize this network. So what's usually thought of as IoE devices are the things we haven't already connected, like appliances, light bulbs, smoke detectors. We're seeing that done now. Garage door openers, things like that, as opposed to the things that have been traditionally connected, like our PCs and TVs recently, game consoles, things of that sort. But all these devices really can operate within the same kind of network. And one of the keys is to assure that there's a reliable home network that covers the whole house. And what you're seeing in the consumer space now is consumers have been motivated to do that already. So they want to use their laptop out on the patio. Maybe they want to put a TV in a room that's far away from their router and get access to Netflix. And so they've figured out how to go get these wireless extenders, power line Wi-Fi extenders. And so a lot of homes now have pretty good coverage wherever they are in the home. And so that's a benefit for IoE devices, because now you bring, wherever you put an IoE device, it doesn't have far to go to connect to a reliable Wi-Fi network in the home. And then on top of that, the smart gateway can provide services like really adding additional security when data goes outside the home. It can manage the bandwidth and the spectrum in your home, and it can do sort of mini cloud services right there in the home, and also communicate to the real cloud services. So we think this reliable home network is a key component for IoE. It makes it easier to bring IoE devices into the home. They don't have to have really as strong and expensive connectivity. They can be lower power, less processing, et cetera. In addition to the basic connectivity, there are protocols being developed out there, such as AllJoyn, which I show here, that allow devices to very easily communicate together across manufacturers and across different PHYs, so that devices can do things like send each other notifications. They can export control methodologies to another device, and this can be done very universally. You're going to hear about some of those things in the next talk, and also later in the week there's one of my colleagues will be talking in detail about AllJoyn, so I'm not going to say much about that today. So one way to illustrate this is you think about, you get this router and you usually have it in your office somewhere, your Wi-Fi router, and if you have you don't even need a huge house. If you got multiple floors, you may want to put a TV far away in a room, far away from the router, and you go get the TV, you bring it home, shit, doesn't connect, right? So now you go back and you get a wireless extender or a hi-fi extender, and now, voila, you've got good coverage out there. So consumers are doing this more and more, And as I said earlier, their homes are getting pretty good coverage. So now when I bring IoE devices in, wherever they are in the home, they have a pretty good chance of connecting reliably to the existing home network. Now, the other thing that the Smart Gateway brings to you is there are other technologies, and we'll talk about those aside from Wi-Fi, that can be used in the home for home automation and a lot of these IoE devices. So one thing that the gateway can support is these multiple connectivity options. Today, most of these non-Wi-Fi options are brought into the home with a separate little box that ties into the gateway, and it basically it's a gateway from the other technology to the internet. We'll talk about what some of those are. So there's a whole ecosystem of technology here, from not only the PHY, but we've defined proximal cloud services. You'll hear about some of that later. Home cloud services that can run in the gateway, spectrum management types of services, security services, et cetera, and then all the way up to the cloud services. So a lot of IoE devices out there are tied to cloud services because you need to get out there to do certain things, and they like to collect a lot of data for you. If you have a thermostat, for example, it can go out and access weather information, so it can adjust temperature based on the weather. Now, today, what I'm going to focus on is really just this bottom layer, just the physical layer options that we have out there. So first of all, I'll talk a little bit about some of the characteristics of these PHYs, because there's a lot of parameters and characteristics that interact in many different ways. And there's lots of trade-offs to be made in the selection of the different technologies and matching them to specific application requirements. Okay, so one thing is, for example, the rate over range. This is important. If you want to have a TV far away from your router, you've got to have enough throughput at that location to pass the video reliably. If you just have a sensor there where you just need a few bytes of data now and then, you don't need as much throughput. You still have to be able to reach there, but at a much lower throughput. So as you get farther away, for a given technology, you lose throughput. It's just a classical digital modulation curve. Now, the other thing that you can do is there are two things you can do, several things you can do to improve this. One is you can increase transmit power of the link. But you can only go so far because all of these things operate in unlicensed bands, and there's regulatory issues for how much power you can use. And that tends to add cost and also consumes more power. Another thing you can do is you can move to lower frequency bands, and that's starting to happen. So Wi-Fi started out at 2.4 gig, and Bluetooth is there, and 15.4 is there, as you'll see. And then Wi-Fi moved to 5 gig, which actually make the range problem worse, but there's a lot more bandwidth up there. So that was needed for other reasons, like reducing the congestion of Wi-Fi in the home and being able to send reliable video streams around the home. But now what's happening is that the technology is moving to sub-gigahertz because you get much better range there. And we'll see some examples of that. Another thing you can do is you can increase the modulation complexity. So a lot of the very simple technologies, use simple FSK, QPSK kinds of modulations. 11N goes all the way up to high levels of QAM to get much higher throughputs in a given spectrum. But the cost is greater and the power is greater. But if you need to get that kind of throughput, you need to go there. Now, you heard in the previous two sessions a lot about power consumption, and this is another trade-off that part of the trade-offs that you make. So one of the things when you're designing an IoE device that you got to consider is, well, what's my power source? And that's determined by a number of things. What's the industrial design? What's the use case? And what's the usability of it? So for example, in a watch, I kind of constrain to a coin cell battery. So that limits, to some degree, my choice of connectivity PHY. For example, you're probably not going to run Wi-Fi 802.11n on a coin cell battery. You can't do much with a coin cell battery over a period of time. And another issue is what will users accept? Sort of the user acceptable recharge replace cycle. So for example, you all have mobile phones and you're perfectly comfortable recharging them every day, but you're certainly not going to replace your smoke detector battery every day. That has to be every year or more. So I think you saw earlier really good presentation of the different techniques here, especially energy harvesting. I really enjoyed that. I think that's kind of a cool technology. I'm looking forward to that expanding. Now, there are some things you can do. There are trade-offs, again, in the different protocols that you select, or the different technologies you select based on their protocols. So you heard a lot in the previous talk about reducing the power consumption of the basic circuits. Okay? What the protocols can do is they can help you reduce power or increase your power. So you have to match the protocol to your requirements. Okay? So some of the key parameters are the transmit power, the receive power, and the sleep power. Another issue is the packet size and the overhead. So when you are transmitting, that's when you're using the most power. So you want to be on the least amount of time. So the smaller the packet overhead that you have, the better. So if you have, for example, an 11N packet where you might be sending hundreds of bytes in a packet, that protocol overhead is pretty minuscule. But if you only send like 1 or 2 bytes for something like a sensor, then that overhead is a lot more than some of the other PHYs. And we'll show you what those are. You also want a protocol that allows your device to sleep for a very long time, like a year if need be, or weeks or months. So if I have a remote control to a TV and I go away on vacation and I come back, I want the thing to work again when I press the button. Okay. The other thing that factors in is the PHY rate when you are on. So again, remember the on time is when you're really going to use a lot of power. You want to be off as much as you can. And when you're in sleep, then you get to the circuit issues that you heard in the other talk. So when you're on, you want to get on fast, and you want to transmit your data fast, and you want to get off. And so I'll show you some examples of that. And then there's the duty cycle of how often do you come on, and how long do you stay on. So here's an example of a typical Wi-Fi device where it's coming up from, on the left, what's called IEEE network sleep. And so there's always a trade-off for these sleep modes of how much power you're using versus how quickly you can actually come up to full level and send the packet, so response time. So in this case, we can come up to, we can send a packet in 2 milliseconds. If we're off, where we're like a microamp kind of sleep power, then it takes us a longer time, 40 milliseconds, to get up and send a packet. So this is important for an application, again, like a remote control, where when the user presses, the remote control might be asleep because you're not using it very much, and then you press a button, but you want a response to that pretty quickly. So this is one of those trade-offs that you have to keep making. And here's an example, for example, of 802.11n, or 11AH, which is a new technology I'll talk about shortly. Because it has a higher PHY rate when you get on, it's on less time than if you're using another PHYs like 15.4, where the data rate is slower. Okay. This is for just a 1-packet transmission, which is typical for a number of IoE devices. And here's an example of how you can match the protocol. You can adjust the protocol, take a standard protocol and play with it to match an application. Typically, these are done in constrained systems where you control both ends. So if I have a Wi-Fi device and I'm just communicating to a standard AP, I certainly can do some power saving techniques, but I don't have nearly the flexibility I have if I control what that AP does on the other side. So this case here is where it's a pretty common case. You have a TV and a remote, and they come from the same manufacturer, and they can control the protocol. It doesn't have to be a standard Wi-Fi interchange. You can play around with it. So what we did here with this protocol is we built a battery life model, and you can plug in what you think your use case is. This is one use case we picked where we said, okay, during the day, during the 12-hour period, the TV will come on for 5 times for 1 hour each time. And then within that hour, we had first the power on, and then we had 60 seconds of button pushing of various kinds. You know, in this case, we were doing gestures. You know, we had accelerometers and gyros in there, and that takes some power. And so we had, you know, like five of those happened in each hour, and you know, you can adjust this to whatever you want. This was just a particular case. And with that use model, we calculated that the battery life of 2 AA's would be about 12 months. So again, you couldn't do this with a remote talking to a standard AP, but when you control the protocol inside the other end, in this case the TV, you can do some interesting things. Okay, security. This is this is becoming actually not a trade-off anymore. Security is going to be a very serious issue for the IOE business, and the industry's pretty concerned about it. You've probably heard about the Foscam hack, where they hacked into baby monitors and were screaming at babies, you know, and trying to wake them up, and it's pretty unnerving for the kids, the babies, and the parents. So security is a really key thing, but it has to be dealt with throughout the whole ecosystem. And so the PHYs actually are doing their part to be sure that, you know, we can enable security over the channel. It has to be used properly. But most of these PHYs have built-in, you know, AES encryption. They've got secure onboarding protocols, with device authorization, authentication, and lots of methods for having secure software downloads, securing the software once it's in there, and also software updates. And you heard a lot about some of that on the processor side earlier today. But it's a really key thing. This could kill the business if there are a lot of crazy hacks out there and people feel insecure. You know, for example, if you thought your door lock could be hacked, would you buy a remotely controlled door lock or a garage door opener? You know, so it's really consumers have to trust the privacy. So this is a big focus of when you select a PHY. Okay, let's talk about the key technologies that are out there then. So again, remember I'm focused on the connected home. So these are the technologies that are typically being used today and probably for the near future inside the connected home. In other parts of the IoE space, in industrial applications, smart city applications, of course you have cellular technology, you know, LTE. In factories, you have things like KNX and Ocean, and there's a broad range of those technologies out there. But in the home, these are the technologies that are at the forefront. So the two granddaddies are really the Wi-Fi and Bluetooth. They've been tracking each other for about the same period of time. So Wi-Fi started out actually way back earlier than this as 11B. And then it moved to G, and then to N, and now we've got 11AC, which was just, you know, released in the last year or so. And so it's a progression of let's go faster, you know, more complex modulation, using more spectrum, and we got to go faster. We got to have gigabit Wi-Fi. So we're there. We got gigabit Wi-Fi, and I'll show you a little bit how we got there. Now, there's a new track, which is, okay, we don't need to go faster for IoE things, but we have to go farther, and we have to have lower power, and a few other things. So that initiated a new standard called 11AH, which is really designed from the ground up to handle small data exchanges. It's a low power protocol, very low overhead, and it's specifically designed for IoE. So it's kind of going away from the let's make it faster to let's make it better in these other ways. And then you have Bluetooth. That started out as a pretty low bit rate device or technology for keyboards and headsets and things of that sort. And that evolved into EDR, which went up to 3 megabits. And then BLE, which is out there today, is the really low power version of that, and is really designed a lot for things like wearables. So these are the two big runners in the market, as you'll see in a minute. Okay. And these run in 2.4 gig band. 11AC runs in 5, and 11N runs in both bands. Bluetooth's in 2.4. And then we have 802.15 technology, 802.15.4, and that also initially started out as a 2.4 gig technology, and it maxes out as 250 kilobits. But it was designed very much with IoE type devices in mind, low power, very lightweight protocol, and it's seen some traction out there. Now I put Zigbee and 6LoWPAN out here because they run on top of this radio. So I think a lot of people were confused. I hear people talk about 15.4 is Zigbee when it's not really Zigbee, it's just the radio. So 15.4 is the radio, the MAC, and Zigbee is a protocol that runs on top of that radio and is known for doing a lot of, for having a good mesh protocol. So this has got traction out there. And 6LoWPAN is a protocol, which you'll hear about later, which runs on top of this radio and gives you IP connectivity. And then we have this technology out there called Z-Wave. This has gotten some traction out in homes for things like sensors and light switches and things of that sort. It runs at sub gigahertz. And so for a given power, it goes farther than the technologies at 2.4 gig. But it maxes out at 100 kilobits. It was standardized in the ITU a few years ago. And I believe 6LoWPAN runs on top of it as well now. It wasn't inherently an IP-based protocol. I should mention that AH is also designed to run in the sub-gigahertz band. So again, it goes farther because it propagates better. And then we have one wired technology, which I have to mention because it's being used in IoE devices. It's called Powerline, PLC. And this started out as home plug at a pretty low rate some years ago, evolved into home plug AV, which is designed to move video streams around the home over the power, your power wires. And now we're at AV2, which has a data rate, a PHY rate of up to a gigabit. And also in this time frame, again, we went down. We went to something called home plug green PHY. So instead of trying to go really fast, we went to more modest rates at 10 megabits, but we focused on, again, lower power. And you say, well, why do I need lower power when I'm connected to the power line? There are a lot of regulations coming that require lower power, and even in devices that are line powered. Okay. So these are the technologies that are used in the home, and if you look at where we are in the market with those, Bluetooth and Wi-Fi are the big runners, but that's because every smartphone. One of the reasons every smartphone has both of these inside, and they've really been around the longest and have seen a lot of applications. Powerline was about 50 million units shipped last year, and Z-Wave, from best I can tell, was about 20 million units shipped last year. And then you can see down here is the 15.4, so it's been starting to grow. So there's a lot of Bluetooth and a lot of Wi-Fi out there. So we think those will tend to be the dominant technologies, including 11AH when it comes in, but some of these others PHYs have some traction as well. Okay. So just to point out where these sit a little bit, I talked about it a little bit, but the 2.4 gig spectrum is where 11N, 11G, well, part of 11N, the 2.4 gig version, Bluetooth, BLE, and 15.4 all sit here in 2.4 gigahertz. So it's a little crowded, but all these PHYs have mechanisms to deal with coexistence. So they cohabitate pretty well. 11N and now 11AC run at 5 gig, and there's a lot of spectrum, a lot of clean air up there, but this isn't typically looked at as a good spectrum for IOE. The IOE is focused mostly here, and now at sub 1 gig. So Z-Wave's already there, a variation on 15.4 called 4G is there, and 11AH is going to be there. Okay. So here you go farther, here you can send a lot of throughput. So this is an example of how these spectrums are channelized. So Bluetooth has like 40 carriers, and it has 3 advertising channels, which it uses as part of its coexistence, and it frequency hops. So it's hopping around, and the devices all sync to one another. So it has pretty good coexistence. It tends to avoid areas where the other PHYs are at a given time. 15.4 and Wi-Fi are single channel systems. You run all in this channel at once. Now you can move around to different channels, and the protocols do that again to avoid channels that are occupied by something else. Wi-Fi gets it's higher bandwidth because it's got wider channels. So it's got 22 megahertz channels instead of 2 megahertz, and it also has much more aggressive modulation techniques. So it can go up to the 600 megabit kinds of rates. The disadvantage here is that there really are only 3 non-overlapping channels for Wi-Fi in 2.4. So that's what was done was to go to the 5 gig channel, and it opened up a whole lot more spectrum. So this is how AC is channelized, and I won't spend a lot of time on this because we don't use it for IOE. I just kind of put it in here for completeness. But you can bond together channels. The basic channel is 20 megahertz, but you can bond to 40 to 80 and even to 160. Although it's kind of hard to do this in practice, but this allows you to do gigabit PHY rates. Okay, just some quick things on comparing some of the basic capabilities of these. So again, 802.11 Bluetooth and 15.4 and 2.4 gig, and the others are in sub 1 gig. So for 802.11, we typically you can get whole house coverage at pretty high rates. You may need repeaters, as I showed you before. But that's really what Wi-Fi was initially designed for. Now, I picked here a 1x1 11N at 2.4 gig, and the maximum rate for that configuration is 75 megabits, but that's maybe more comparable to what you'd be using in IOE. And Bluetooth technologies tend to be, they're short range, more in-room technologies. You probably all have Bluetooth devices, and you can't connect usually across rooms. They have more modest throughputs, but they're perfectly fine for the kinds of applications they're targeted for. 15.4 is designed to do whole house, but usually with mesh. So you build Zigbee on top of this, and you can get home coverage with a mesh. And then the 1 gig versions get whole house coverage too, because they got better coverage because they're in the lower bandwidth. And these are the maximum data rates over here that they provide. Now, you almost never see those rates, in a typical configuration, but that's the best you could do. And then on power consumption, basically sleep currents are all around the 1 microamp range. I mean, this was just some typical examples. You can actually get this down in that same range as well. And they all have similar transmit-receive powers. So where you get the power consumption benefit and differences is really in the other aspects of the protocol, which is the you know, the header overheads. I've used MAC headers here as a proxy for the physical frame. And then the phi on time. So that's related to the phi rate. So you know, 11N has very short on times. 11H has short on times, and the others tend to have longer on times. But some of the other protocols have light overheads on the packet, so that adjusts the other way as well. So for streaming applications like video, Wi-Fi can support that, 11N. The 11H can support that to some degree, and the other devices, Bluetooth can do audio, but basically the others are not designed for streaming. They're really designed more for state and control kinds of applications, which is largely what a lot of these IoE devices want to do. You know, just send a few packets at a time. Interoperability, most of these have certification bodies. There's the Wi-Fi Alliance certifies Wi-Fi, the Bluetooth SIG certifies Bluetooth, and then if you're using Zigbee on top of 15.4, that also has certification. These all can support IP connectivity, most of them, some of them natively, and others with CIST on top, like 6 low WIPAN. And in terms of network scalability, how many nodes they can support, for practical purposes in the home, for the applications they're targeted at, they can all support sufficient number of devices, we think. Okay, so let me just say a little bit more about 11AH. So this is a technology that's coming soon. You'll probably see products for sure by 2016 and perhaps even next year. The draft 2.0 was just approved. So some of its key advantages are because it's in sub gig band. It has much better range for a given transmit power than 802.11 does, 802.11n. And it's been designed from the ground up to support, you know, low battery or good battery life with even coin cell types of batteries. It's very flexible, as I'll show you in a minute, in its the trade-offs of channelization and throughputs and its capabilities. It supports thousands of nodes, 8,000. It's got innate IP connectivity. And it's actually good for outdoor coverage around the home. So if you want to, you know, cover your large yard with this, you can do that as well. One of the only minor issues with it is that the spectrum is different in different regions. So I put this out here just so you understand that. In the U.S., we're in the 900 megahertz range, and Korea overlaps us, as does Japan. The EU has a narrower band here between 863 and 868, and China's over here, and you can see the maximum power requirements that you're allowed over here. So this makes it a little more complicated to design the radio and go get all the certifications and things, but we're pretty used to doing that, so it's not a huge problem. And this shows how it's channelized. It has a lot of options, just like AC has a lot of options. You can go anywhere from a 1 megahertz to a 20 megahertz channel. And of course, as the channel gets broader and the modulations get more complex, you can support higher throughputs. Probably most IoE type devices are going to run with the 1 and 2 megahertz channel kinds of configurations. And this just illustrates, this is a model of the distance advantage it has over 11N in particular. So this was a simulated case of we wanted to sustain a given bit rate, a peak rate, and then an edge rate of about the same. So this is 5.8. It's not exactly the same, but it was actually some testing that we did. So it just illustrates the additional range you get with these sub-gigahertz technologies. Okay, so where are these PHYs used? So just to kind of summarize, so BLE and Bluetooth, they're very low power, modest data rate, and tend to be short range. You know, Wi-Fi, very high data rates. You can get very good range, especially with repeaters. But they're not as power friendly as the other devices. But if you need the throughput, you need to go there. 15.4, modest data rates, good power profiles. When you combine it with mesh, it has some very viable implementations. Z-Wave, very low power, pretty low cost, very modest data rate, and also has the better range because it's sub-gigahertz. And 11AH, we think, kind of brings the best of all worlds in here for IoE type applications. So we'll see how this rolls out in the market over the next few years. And home plug green 5 off to the side there. If you've got a device that has line power, this is a perfectly reasonable solution as well. And we see customers using both power line and a wireless technology in the same device frequently. So in terms of specific devices, if you want to send video or media streams, you're really going to want to use 11N, 11AC, or power line. If you're going to use, for a device like a mobile phone or a tablet, it's going to be Bluetooth and 11N. You see 11AC there. Actually, you'll soon see that in phones, and 11AH. For life management types of devices, wearables and things of that sort, there you've got to really go to the lower power options like Bluetooth and 11AH, I'm sorry. And that's also tied to what's going to happen in the mobile phone business, because a lot of the wearables technologies will communicate away from the body through your smartphone, using that as a gateway. And smartphones are going to have Wi-Fi, Bluetooth, and eventually 11AH is going to be in there as well. Probably won't be seeing Zigbee and Z-Wave in many smartphones. But for home operations, things like thermostats and garage door openers and things like that, you've really got these 4 options that can really apply. 11AH, 11N, the Bluetooth, the Z-Wave, and the 15.4. So there, it's really up to the market and the applications to decide, which ones are gonna do well. So thank you for your time, and I think we'll have questions at the end for all of us at once. So we'll move on to the next one. Thank you.
Okay, thank you so much. Still have, okay, now I think we are sort of on time. So the last speaker is Bill Curtis from ARM. He's a lead strategist for Internet of Things, and before ARM, he was a senior fellow and design engineer at AMD. And before that, he was a CTO of Dell's Consumer and Display Groups. And before that, he was the director of computer sciences for Landmark Graphics and Halliburton. He's going to talk about IP standards for IoT devices. And remember that after this talk, we're going to have an open session, sort of an open panel for questions with all the speakers. Thank you.
Yeah, there's beer after that too, right?
There's actually wine and cheese.
Wine and cheese. So the only thing between wine and cheese and you is me. IoT standards. You've heard something about that. My goodness, let's you've heard something about that kind of in the past few talks. We're going to take a different cut through this. Instead of looking at the radio standards, we're going to look at software. I know it's primarily a hardware conference, but bear with me. I think you'll find it interesting. But first, let's back up a little bit. IoT isn't new, and a lot of the times people talk about IoT as if it were. It's really not. It's just the things around us becoming smart and connected. It's been going on for about 20 years, and the Mark Weiser quote, I don't think anybody has given that yet at this talk, so I'll be the first. Mark Weiser said in 1991, Ubiquitous computing. The most profound technologies are those that disappear. They weave themselves into the fabric of everyday life until they're indistinguishable from it. And that's really what IoT is all about. Over 20 years ago, we've been working on this a long time. In 2010, the number of connected things exceeded the world's population, 6.8 billion at the time. And there's a watch, there's a pager watch that was done by Motorola 17 years ago. You wear it around there and you get, remember pagers? And who wears a pager? But people did back then. And when you think about it, that was really a wearable. It's not much different than wearable watches that we see today from big names like Samsung and stuff. So these types of devices, they're not new. But what is new? What's new is that they really are becoming part of our everyday lives instead of kind of gadgets like that. So how are we going to get this acceleration going on here? I mean, if you look at what the analysts say about the Internet of Things, it's going to grow very rapidly. But the situation we have today is that IoT solutions tend to be application specific. So you make a device and you write software in the cloud or on your phone to go with it, or both, and then the device and the software functions as a system. Well, let's say you want to write different software for that device. Very difficult. Or if you want to produce a different device to work with that software. In other words, interoperability isn't where we want it to be. So that results in closed supply chains, proprietary interconnects, and very limited plug and play. So despite all this, current trends show fairly strong growth. And let's see, it's really hard to read that. 8.7 billion was the Cisco number of connected devices in 2012. By the way, that's a CAGR, as I recall, of about 13% compound annual growth rate. But the analysts are predicting much larger growth rate for IoT. 30, 50, 75 billion. What do you believe? No matter how you look at it, that's a big change from where the current trends are heading. What's going to fill that gap? What's between the blue and the red line? So what we need to do is figure out what has the potential to drive the demand for many tens of billions more devices. I mean, that's somewhere between 10 and 50 billion, something like that, additional devices, depending on which analyst you believe, between now and the end of the decade. That's where those numbers point. And we've heard today a lot of good news about new platforms with integrated wireless that goes down under 10 milliwatts, transmit receive, while in operation. Right-sized processors, memory, low cost, low power, secure, trustworthy. Well, today, is everything secure and trustworthy? Probably not. But the good news is a lot of our partners are building chips that really are and have secure storage and adequate security provisioned onto their SoCs. So there's hope that the platforms are going to get there with cost, power, security, fairly easy software development, and easy integration into things. They'll have the power profile and the size and things like that we need. So there's reason for hope that blue curve will turn out to be real and not a myth. Now, we also need internet scale for the ecosystem, and there we have a lot of work to do. What we want is standards-based connectivity, not just the radio, but the stuff above the radio. Standards-based provisioning, so that you can take a device and provision software and keys and secrets on that thing remotely, and do that independent of the value chain of the specific device. That'd be great, wouldn't it? Then you can have an open market for devices and an open market for software. That's what we want these standards to give us in the long run. And of course, end-to-end security, where you can pass packets all the way from the devices up to the cloud or to wherever it is the applications run. That's worth noting. Sometimes people get wrapped around the axle on where the software runs. Oh, it's going to be running in the cloud and controlling the thermostat in my house. Well, maybe and maybe not. Software can run anywhere, and we don't want to be really prescriptive that this is a cloud-to-ground solution. It's a wherever you want to run the software to ground or to device solution. That's worth paying attention to, and there's a few slides on that later on. So, taking a step back, platforms, all wireless, pretty much for IoT, right size, low cost, low power, secure, easy development, easy integration, check. We've got line of sight to making that happen. The ecosystem is different. Busting these silos is going to be a little more difficult. Well, and so let's look back a little bit. 40 years ago, we've seen this happen before, so let's look back. 40 years ago, internet technologies displaced proprietary interconnects. 25 years ago, thanks to Tim Berners-Lee, we got web technologies, web applications, and the miracle there was 100% reach. Now we have a client and a set of protocols around it that let us go, let us build web applications that everybody can use, so any browser can get to the data. It ended the closed client-server ecosystem with technologies that were 100% reach. Then the mobile revolution happened, beginning when Apple released the iPhone. But when you look at what they did, it wasn't the individual technologies in the phone that were significant. It was that, in my opinion, it was that the phone gave you access to the internet. Multi-touch technologies have been around for years, since the 1980s. And if you look at the processors and everything else that were in the iPhone, they were there, and they were instantiated in other products long before 7 years ago when the iPhone came out. They just did a really great job putting the software together, making it usable, and opening it up to the web. So that's an obvious strategy that we can follow. Hey, we can get scale in the IoT by following the internet model. Use open standards, enable independent development of solution components, and go for 100% reach. So you can build applications and devices that can connect with one another. But there's some complexity here because these IoT platforms are constrained. Low power, low bandwidth networking, small, staccato, they're off most of the time. They wake up, they send stuff, they go back to sleep, sometimes for a long time. And so it's difficult to use internet protocols as we know them today in this world. So the good news is people have been working on this for like 7 years or 7, 8, 9 years or so. And as a result, we have plenty of IoT platforms to choose from. There's 120 of them right there. By the way, when I give this talk, this is the #1 slide people want. And then they come up afterwards and they say, hey, you forgot one. And it's the one that they're on the board of or something like that. So, hey, come up afterwards, I'll make the notes, I'll add it to the next version of the slide. But the point is and this isn't just a random list of standards. These are ones that are actually relevant to what we're trying to do here in the Internet of Things. So how do we make sense of that? I mean, no one can make sense of 120 standards. What are the ones that really count, that are going to open this ecosystem and give us Internet-like scale? Well, here's one way to look at it. This is a taxonomy sort of thing, right? So there's the application sitting on top and a big green box for standards. So one way to cut it is to say, all right, we've got standards at the application level. Underneath it, we're going to do things web-like, right? Because that's been proven to scale before in the past. Then they're going to be supported at the internet level, and then finally at the network level. The previous speaker talked about the network level standards. So how do you cut through this? Well, let's start here with the stuff that works now. On the bottom, we've got Wi-Fi and cellular, and that's, of course, 802.11 and various flavors of LTE, 3G. And on top of that, our old friends, the internet standards, that date back 20 years, TCP, UDP, and IPv4v6. Yay. Then on top of that, web level, HTTP, TLS, thank you, Tim. On top of that, we have RESTful interfaces, and we have RPC, RMI, Remote Procedure Call Method Invocation, that can sit on top of that stack. Sometimes kind of going through an HTTP-like stack, and sometimes going directly to sockets. So there's kind of a controversy about should you always be RESTful and use the web protocols or not. But however you look at it, on top of it, there's a whole bunch of application level standards that build on top of all of that stuff and try to achieve the kinds of interoperability tricks that I was talking about earlier, where devices can talk to servers or talk to one another and do it in a very, very open and standardized way. And we'll talk about some of these during the talk today. But that's not the only network layer or that's not the only stack we need to be concerned about, because Wi-Fi and cellular are for higher performance networks and devices. Now, Wi-Fi is going to add another way to communicate with low power in the future, but I'm not going to talk about that today. What we do have is Bluetooth and Zigbee, which we talked about in the previous talk. But each of these has their own stack that extends all the way up to the application level. And it's not HTTP, it's not TCP/IP, it's a different way for applications to get to the APIs they need to communicate with the devices. Nothing wrong with that, it's just not web-like. Obviously, there's a gap in the middle there. Oh, I'm sorry, those are for constrained devices, of course. That's what's different about Zigbee and Bluetooth, is they'll work at very low power levels with your cell phone or in the case of Zigbee, across your home in a mesh. There's something we can stick in the middle here now that we're pretty excited about at ARM. Two things, actually. It's a mesh network that uses the 802.15.4 MAC PHY level. So in other words, it uses a Bluetooth-type radio. But it's designed to work with the internet protocols, with real internet protocols that expose RESTful interfaces on top, so they look just like the other types of nodes that are connected with Wi-Fi or cellular. So from an applications perspective, you can use RESTful calls and discover the resources on these devices, manage the devices, and deal with them on the network just as if they were Wi-Fi or something else. The thing that makes that happen is the constrained application protocol CoAP and a special version of TLS called DTLS, which secures that traffic. That's datagram TLS. And that's an older standard. Doing security on UDP has used DTLS for many years. You put CoAP on top of that, and then you have a stack that extends all the way down to these constrained devices. Thread is kind of a new standard. It was just announced. ARM is participating in this standard at the board level. Thread was announced in the middle of July, so it's brand new. And the idea here is to take 6 low-pan addressing and UDP and make that, put a logo on that so that manufacturers can build devices, software can support these devices. So you get the advantages of mesh network with IP addressing. And with CoAP on top of it, then you get RESTful web-like interface all the way to the top. Now, as was stated in the previous talk, it's really nice to have a mesh, because then all of your light bulbs, light switches, security sensors, whatever you have in the house, can all communicate with one another, and the traffic can find its way to the nearest access point. So the more nodes you have in your house, the better it works. So you get whole house coverage, and the more stuff you add, the better coverage you get. So there's a lot of things to like about mesh networks. So if you take a step back and look at this, there's ways you can deal with constrained devices and networks. There's ways you can deal with higher performance devices and networks. And in all cases, you can use RESTful web-like protocols to get to all these devices. So when you think about it, that's really internet and web to the edge. And with Thread, you also add constrained devices and constrained networks to that capability. And then, not to forget, Bluetooth and Zigbee are still useful, and they'll be around for a long, long time. They just don't do the IP web thing. So that's how to read this chart. Okay, so Constrained networks for IoT, just to summarize, BLE, Bluetooth Low Energy, is personal area networking, hub and spoke, works with your cell phone. You all know what that is. 15.4 is a mesh topology. The consumer version of that is Thread and Zigbee Pro, which is the version of Zigbee that's used for like light bulbs and things like that. There are industrial versions, Zigbee SE, Smart Energy, that's used for electric meters, and Zigbee NAN, neighborhood area, which is used for street lights and stuff like that at sub-gigahertz frequencies. The challenges for these constrained networks, they're slow, they're sleepy, in-order packet delivery is not guaranteed, they drop packets all the time, the nodes are asleep most of the time, and they have problems with multicast. Other than that, they're perfect. So let me say a few words about Thread, just a few. This is not a talk about Thread, I just wanted to mention it because we get questions about it all the time. Why do we need Thread? Whole home coverage, low power radios, coverage increases as devices are added. And the options today, Wi-Fi, Zigbee Pro, Z-Wave, Insteon, and a whole bunch of proprietary stuff, Bluetooth and BLE variants and others, all great stuff, but none provide that list of features that are listed there. Efficient mesh, open protocol, whole home, low power, resilient, no point of failure, and totally open and free. You add all that up and there's really nothing. And that's why on the previous speaker's chart, the 15.4 line was pretty flat compared with the others, and we're trying to change that. I think in order for the Internet of Things to grow, we need to see one of those hockey stick type curves on 15.4 mesh radios because they're just very useful. So here's the marketing literature about Thread. Won't spend much time on that. Thread is for appliances, access control, climate control, energy management, thermostats, lighting, safety, security, that kind of thing, a mesh network. And it's built on well-known standards. It doesn't have anything, it doesn't care about the traffic that runs on it. It's like your Wi-Fi router for low-speed devices. That's really what it does. It routes packets, specifically UDP packets. And it's all based on IP and 6LoWPAN, which we'll talk about in detail here in just a minute. And it's based on the 802.15.4 MAC and PHY that have been around for years and years with Zigbee. And the status is this thing is under development. We'll have certified products on the market as early as next year, because in some cases, in many cases actually, there are already products that are running the 15.4 stack, and they're just, or 15.4 radios, and they're just waiting on a certified Thread stack in order to turn on Thread. So we don't believe this will be a very long time to market. In other words, we think this is going to happen very quickly, and the Thread group is gearing up for that. You have any questions about Thread? There's threadgroup.org, or send me an email. Okay, enough about Thread. So why is it so important that we talk internet all the way to the device, all the way to the edge? Well, like I said, we want this web scale growth for IoT, including constrained networks and devices. That's really important. We want that scale and growth. And there's two parts to that, the IPv6 part and the web part. V6 is really important. IT to the edge, internet to the edge, IP, is important because it is the best, most suitable framework for IoT. And there's a reference at the bottom for a paper that I thought was particularly good that details why you want to use IPv6 for these types of use cases. I mean, V6 was really intended for mobility. It has a lot of features in there that make mobility possible. It's mobile, it's secure, it's open, it's global. And you can, if you're worried about V4, of course, you can just tunnel it. So using IP for IoT is just a slam dunk. It's the right way to do it. Now, we can also make it web-enabled. In other words, we want this web-scale development. That's the client-server computing with 100% reach thing. So we want to use web-scale standards and design patterns and tools with a RESTful application interface. Now, what this gives you is really interesting. It means you can discover devices, and you can discover the characteristics of those devices and the resources that they have without any a priori knowledge of what the device is. That's really important because otherwise you're locked into these silos where you have to design application support into code that runs on servers or gateways, and you have to design applications to work specifically with those devices. We want to break that up and make it possible to separate those parts of the value chain. It also makes it possible to using standards-based technologies, manage the provisioning of those devices and deposit software and keys on there and do that securely, and do that from anywhere that you can get an IP connection to the device. That means you can deliver devices to people, and you can contact the device through the internet and make the device do what the person wants it to do without having to do complex installation procedures inside like a residence or something like that. Lots of reasons why you want internet to the edge and web to the edge. Okay, so how do we do this? Because the web was designed for IPv6, TCP, HTTP, TLS, that kind of thing, and that's not what we're going to get with these low-power devices. So, and why not? Well, V6 is inefficient over constrained networks. It's got this 40-byte IPv6 header, which is a full third of an 802.15.4 packet. Bzzzt, kind of doesn't work. Transport. TCP is just impractical on unreliable networks, and it fails completely on sleepy platforms, that are asleep most of the time. You can't just communicate TCP/IP directly to one of these sleepy nodes. It just doesn't work. HTTP, everybody loves it, but it requires TCP, so that doesn't work either. And then TLS secures it's what we use for securing our banking transactions every day, of course. We use it on the internet all day, every day, but it requires a reliable in-order packet transport, which we don't have with these constrained devices. So what's to be done? Well, here's a slide that we use to kind of explain at a very high level what we need to accomplish. The addressing problem is handled by 6LoWPAN through header compression. I'll show you how that works in just a minute. TCP, well, you don't have it with these constrained devices, so we use UDP, datagrams, with no guarantee of packet delivery or order. Now, that means we can't use TCP. Instead, we use something called CoAP that was developed beginning about 7 or 8 years ago, actually. This has been under development for a long time at IETF. And it gives you HTTP-like REST semantics protocol from the application level, and then does the right thing to communicate with these communicate restfully with these very constrained devices. So it's the connectivity piece that you need, so that you take a network that doesn't support HTTP and you make it look like it does. And then finally, instead of TLS, you just use DTLS, which is datagram version of TLS over UDP. And so now you can do stateless security. So then there you see the kind of a cartoon of a reduction in the size of the packets that we have to deliver between the application and the device. Here it is on the left with HTTP, TLS, IPv6. That gets squashed down as we use CoAP and DTLS and begin to deliver binary web objects. And then finally, as we squeeze the header fat out of IPv6 and go to 6LoWPAN, we go from really kilobytes down to tens of bytes. And then where does that take place? Like I said earlier, we really don't care. There's a proxy, which can be thought of as a router or an access point or instantiated in a server in the cloud. It really doesn't matter, because you're running internet type, internet web protocols on either side of that router. So it doesn't matter where it is. The whole thing can be instantiated in your house or on my laptop computer or yours, and you can split this up however you like. So on the left is the constrained internet, or the constrained device world, still speaking internet web protocols. On the right are the applications that try to get to it. And in the middle is the thing that does the translation, and it can run anywhere. So let's look at these technologies one at a time and just click through them real quick. 6LoWPAN is IPv6 low-power wireless personal area networking. Improves the efficiency of the addressing scheme for IPv6. That's what it does. So here's kind of what it looks like, and there's some detail in this slide. it's hierarchical in that it's on top IPv6, on the bottom it's 6LoWPAN. It uses IPv6 addresses throughout. There's an edge router that performs that header compression and hides the node constraints, and the nodes can either be just host nodes that don't route anything, or they can be router nodes that are able to route traffic for other nodes. And as I said before, IPv4 support is of course possible by tunneling. So 6LoWPAN is IPv6, but it doesn't preclude the use of IPv4. Here's a cartoon showing the way the compression actually works. On top is the way things are well, let me back up a little bit. That is a 802.15.4 frame, and they're 127 bytes in length. The IPv6 header is 40 bytes. You know, it's like a third of the packet. So we got to get rid of that in order to get better use of our 127 byte frame. And so when we say compression, well, that's what we do. It's not really compression. We just get rid of the whole thing. We don't use, on the 6LoWPAN network, we don't use the IPv6 address at all. Instead, we use the MAC address as a proxy. Then we compress all the other stuff. We take the MAC address and squeeze that down, and all the other little components in the frame, squeeze them down as much as appropriate for the network that we're building. And then that just about doubles the payload size. So that's it for 6LoWPAN. It's really simple. People are often confused and think that it's doing some fancy compression trick or something. No. It's not really compression. We're just getting rid of stuff. And by doing so, we take an IPv6 addressing scheme and make it appropriate for these constrained devices. Security, like I mentioned, it's just DTLS. It's been around for years and years. TLS, transport level security, is the most widely deployed protocol for securing network traffic on the internet today. It uses, but that requires the use of TCP. DTLS is datagram security designed for UDP. So EDTLS is a kind of a further constrained version of DTLS for very small embedded devices. And there, it's really just DTLS, but the implementation choices that were made were appropriate for small embedded platforms. And this is a work in progress, but watch that one. It's extremely handy for building these little constrained networks. And as always, you gotta have some security. The question is, how much can you afford, both in terms of hardware cost and provisioning cost? Higher security means higher cost, but under no circumstances can our industry afford to produce totally insecure IoT platforms. And if you do some searching on the web, you can find some horror stories about companies that have done that. I won't repeat them here. Some of these people are our partners, so we certainly wouldn't want to do that. But there is some scary stuff out there, some devices that have been manufactured without adequate thought for security. The good news is that I think I mentioned this earlier, a lot of our silicon partners are building new IoT class silicon that has a lot of nice security features built in terms of secure key storage, encryption blocks built into the SoCs and stuff like that. So this is going to improve over time. The efficiency will get better. The power hit that you take for doing encryption will pretty much go away. So how much depends on what you're protecting. Are you protecting a hydroelectric dam or the dog food feeder? Sort of up to you. But no security is I mean, an IoT device with no security is unacceptable. Okay, CoAP, the Constrained Application Protocol. This is probably the best way to look at it right here. It's really, really simple. Well, it's actually quite a lot of software, but conceptually it's simple. Transport, it's comparable to HTTP. HTTP, the transport's TCP, CoAP, it's UDP. Message confirmation is always there with HTTP because it's running TCP transport. So all messages are acknowledged and they have to get through. And that's certainly impossible with these constrained networks. So CoAP's implementation takes up the slack. Like I showed on that diagram earlier, the applications talk to CoAP. Wait, what slide's next? I don't have it in there. Applications talk to the CoAP proxy using HTTP typically. And there it works like any other HTTP service. You know, you get acknowledgement of every message, you communicate with it restfully. The CoAP proxy then does whatever it has to do to make the right thing happen with the devices underneath. And there's caching and storage built into the CoAP implementation so that it knows about the devices that are connected to it, knows their characteristics, and has caches of the information so it can immediately respond to the HTTP RESTful request while being lazy about how it contacts the underlying devices. So CoAP is just a buffer and a proxy so that you can use RESTful semantics with these constrained devices. And when I say RESTful, that's representational state transfer. 13 minutes. I don't think I want to go through this in detail, but RESTful is the HTTP client-server programming style. And please read Roy Fielding's dissertation if you haven't. It's excellent. Still valid today. This is really how the web works. And so when we say web to the edge, this is what we mean. We want to adhere to these kinds of design principles because they have proven over the years to scale. The central concepts are resources, which is anything that can be named, interfaces, simple, basic client-server communication. It's get, put, post, delete, just like HTTP, just like you're used to. Representations is just the state of a resource. And then you can use whatever you want, HTML or whatever, to transmit that information. And lastly, hypermedia-driven applications. This discoverability thing for IoT is huge because it's the thing that allows us to separate the functions of the supply chain and allow things to be dynamically discovered by applications. And this is probably the best and most standardized way to do that. So just to summarize there on CoAP, CoAP is RESTful interface for IoT. The implementation is CoAP. That's the thing that does the buffering and the translation. The resources are uniform identifiers, anything with a name. I mentioned before, get, post, put, delete. Not application specific. There's nothing application specific in the protocol. Doesn't care. CoAP can talk to thermostats or cars or bicycles or whatever is connected to it. Doesn't matter. And there's the features. You can read those later. It is standardized, by the way, and it is an industry standard. It's free to use, and resource linking, resource discovery and linking. I keep coming back to that. RFC 6690 is the place to go if you're interested in that. So let's move up the stack a little bit. I mentioned management a couple of times. So how do you do that? CoAP is just this sort of HTTP proxy. So what do you put on top of that to actually manage the devices? Well, lightweight M2M is an OMA standard. That's the Open Mobile Association. It's a server profile for IoT middleware. So what it does is it's really, really simple device management objects, and it's APIs for how you onboard and manage the devices. Then on top of that, IPSO, IP Smart Objects, is another standards organization. Smart objects are built on top of lightweight M2M. These are composable and extensible objects. Very, very simple object framework that lets you represent anything you want. The data that the device has, the keys, the way you manage it, whatever. It's ways of encapsulating data through this RESTful interface that let you talk from application to device. So this is the stack that we're recommending that you use for talking to these low-power devices. Here is the reference architecture for OMA lightweight M2M. The web applications are just applications you write that use the RESTful interface. There's the lightweight M2M server, which has CoAP underneath it. It contains a resource directory, like I mentioned earlier, and can be implemented anywhere, cloud or gateway. It doesn't matter. And then there's the lightweight M2M clients, device abstraction through CoAP. So they sit there underneath this CoAP thing, and the devices can come and go and behave in a very sleepy way. And there's the services that they provide. Here's how the interfaces work for bootstrapping. Bootstrapping is the term that we use for how you initially configure a device after it arrives. You put in some application-specific code, keys, and that sort of thing. In some cases, there's secure elements like smart cards and things like that. There's a registration interface, again, 6690 based, a management interface, and a reporting interface so that you can have the device talk back to you. The object model is just dead simple. I won't go through this, but it's basically just an integer representation. The client has objects. The object is a collection of resources. The resources are atomic pieces of information, and there's just integers that let you navigate through that. Just as simple as it can be, and it's very compact. So, as promised, I'm going to end a few minutes early in consideration of your wine drinking time. You can buy me a glass of wine later to thank me. We believe standards-based ecosystems will accelerate IoT growth. In fact, we believe that is the only thing that will accelerate IoT growth. We have to get from 120 standards down to some small number and decide how we're going to do this. Constrained IoT devices should be a big part of our consideration on which standards that we really want to land on here. They're going to account for the large part of this projected 17 to 31% IoT industry compound annual growth rate. And web to the edge is a term that I'd like you to remember. I'm talking about stuff that's based on the same industry standards that we use on the web every day. The protocols are like, but for constrained IoT devices. And in order to account for that constraint, the standards that we're using at ARM are IPSO, that's the IP smart objects that let us encapsulate generic object types. OMA lightweight, that's the management interface that communicates through CoAP down to the device. CoAP, the constrained application protocol, that lets you pretend you're talking HTTP when actually you're talking to a really slow and sleepy device. And then 6LoWPAN that gives us IPv6 addressing all the way to the bottom. And then that works over Wi-Fi, Thread, and Zigbee NAN. Did I mention Zigbee NAN? Zigbee NAN is neighborhood area network streetlights and stuff like that. So with that, thank you. Oh, one more thing that I think I forgot to mention. The notes for these slides and the booklets that you have don't match these slides, as I'm sure you figured out by now. If you want a PDF of the presentation, God, I hate to say this, I know what's going to happen. Send me an email. and put something in the header in the title I can recognize, like hot chips. Thanks. Oh yeah.
Okay, so as promised, we're going to have a Q&A session now with all the speakers. So I invite all of them to come here. And if you have questions, please use the mics. Of course, you have two options. Either wrap up now and go for wine, or we could continue.
Do we get to vote?
Or one of them said you could bring some in, and I don't think the organizers are going to allow that, right?
That's right. Yeah, nothing more water. We can talk outside. I mean.
With wine.
So please, first question on the left.
Okay, this question is for Bill. There's one protocol I have heard called XMPP. Of course, that has been in use for years too. I didn't see you mention that part. I'm not clear exactly XMPP would play any role in the future, but on the other hand, I would really appreciate some of your clarification for that one in specific.
Yeah, that's an excellent question. It's an inexcusable omission from my presentation. It is a publish subscribe protocol, that sits alongside the stack that I just talked about. So there is a relationship between CoAP and MQTT. Well, I'm actually on, I think. You guys need this. And one way I think this is going to progress is and Zach Shelby and I are talking about this right now to try to figure out exactly what our position is going to be on this. And we're also talking to the folks at IBM that had a lot to do with you're talking about MQTT?
No, XMPP.
I can't hear you very well.
Sorry, it's XMPP. That's for instant message.
No. I don't believe that's related to what we're doing at all.
Okay.
And I do apologize. I really misheard your question.
Oh, I mean, the other question is about MQTT too.
I can answer that one. but the MQTT is a publish subscribe thing that'll sit alongside CoAP. And so the idea is to modify CoAP or to enhance CoAP so that there is a kind of a CoAP pub sub or a CoAP MQTT or something like that, so it'll work either way. So we already have a proxy in CoAP. There's no reason it can't be expanded. And in fact, in the lab, we already have it working to work with MQTT as well.
Well, what kind of process would there be to really reconcile?
Yeah, I'm sorry, I can't hear.
Okay.
I cannot hear you.
Could you please repeat the question?
What kind of a reconciliation process would that take to resolve the potential differences between MQTT and CoAP?
Well, really, it's not a reconciliation. There are two different standards and two different ways of communicating between devices and servers. One is publish-subscribe, where the MQTT device sends information up to the server. The other is a very much web server-like query of the device. So it's really kind of there's no reason that they can't both be accommodated within the same proxy software, and that's exactly what we want to do.
I have to let other people speak. No, you stepped out of camera. Oh, I'm sorry. The question I had was really initially started from the utility world, because oh, okay, I'm sorry.
There's a bad echo up here. It's very difficult here.
The utility world seems to, especially on the other side, it will be the industrial automation world. They tend to have all these clunky things and with $1 billion of asset spread it all over the world. So they were questioning, first thing is, do they really want to adopt all these new inventions? On the other hand, they also realize that IoT is the way to go, that it doesn't seem to have another way out. So that's why I was really wondering if you have more insight into how they would really adopt this thing. Because, for example, like Echelon is, Honeywell and all these companies have entrenched protocols already in there.
Well, they'll only do it if it makes business sense for them to do so. And I think I mentioned earlier in my talk that a lot of the connectivity schemes that are there today will remain for years and years to come. We're talking about accelerating the growth rate of the entire industry. And stuff that's already in place will only get replaced if there's a good reason to do so. Okay. So if IoT isn't bringing additional value to industrial customers, then they'll just simply stick with what they have.
Thank you. I'll let other people ask questions.
Thanks. Sorry, by the way, they turned the speakers up back here. It's much better now.
Okay, I have a shorter one, I hope. I asked this of a wireless sensor network panel a few years ago, and since we had security this morning and you've talked about it some, my question was, okay, say some more about what's going to happen to avoid the moral equivalence of spam and viruses. Now, they all gave me good answers, but Chris Peaster of Dust Networks ended with the best one, which was, we've worked very hard to have better security, but yes, someday you will wake up to find your fridge has sold Viagra to your microwave. So how are we going to avoid that?
You guys want to take the first crack at that? Well, here's an. I do.
No
have
one wants
thing.
to answer.
I do have one thing. I heard another good one like that. It was the Internet of Things is the largest attack surface ever devised by man, and that's probably true. So that's why we've got to be absolutely, completely diligent about implementing reasonable security at the appropriate cost point. That doesn't mean burden every device with massive amounts of security infrastructure. It does mean you have to have the appropriate amount of security and just not do dumb stuff when implementing all of this stuff.
And probably security has to, of course, go through all the levels down to the chip level, which means that every chip needs to have some sort of unique way to be identified. For example, a cheap way to do that is a physically unclonable function, and that's a reasonably active research area these days.
So, I mean, these problems are being worked on, but they, you know, to some degree, they relate to the value that you have to have in security. I guess a good, and the effort you spend on, I guess a good example might be the digital broadcast TV business, you know, satellite TV, cable. They went to incredible lengths to develop conditional access systems and had security all throughout the chain, including, you know, inside the chips. But there was huge economic value for them if their programming was lost. So when you talk about you know, a smoke detector or a garage door opener, there's not a lot of not a lot of value there to go pay for really extensive over-the-top efforts on security. So I think it'll be measured by the particular product. But there is a lot of work being done on for the basic mechanisms to be there to enable that. But it's a long ways to go.
Well, I'm coming here as a software designer. Sort of intrigued by the challenge of writing software for unreliable or low-power devices. And it occurred to me one useful thing that the hardware developers could provide would be, you know, perhaps just a register somewhere with bits indicating what the current state of the machine is. In other words, we're in a low-power environment. We're missing cycles. You know, give us some sense of what the current degradation is, and then the software could simply monitor that and make appropriate decisions. So if it's full power and there's a lot of reliability, you might do one thing, but if you're in a sketchy environment, then you might choose to run different code or do things more redundantly at the software level, something like that. If that was built into the chip itself, that would make the software developer's life a lot easier. Part of the motivation here is Martin Renard, Professor Renard at MIT, has done some curious sort of out-of-the-box experiments with software. So one of them is if you discover that a pointer in an array is out of bounds, he just puts it at some random place inside the array and continues on. And the amazing thing is it almost always works. Okay? If you're in a loop, and you're using too much, it's taking too long to get something done, he'll skip maybe 7 out of every 8 iterations. Just increment the counter and go back around. The end users almost invariably can't see any difference. So there, you know, there are these very unexpected things that you can do at the software level where if you knew what was going on at the hardware level, you could maybe help things out a bit.
Are you asking about knowledge of how well the network's performing and how congested it is?
Maybe, but I was thinking more in terms of the chip itself. So you were talking about approximate computing, that when you get below the threshold, you know, when you get into timing errors where your instructions are not being executed properly, if the software could just monitor that, it might be able to skip every 7 out of 8 loops to you know, to put less of a stress on the system until the chip looks better again, and then go back to the normal mode.
Massimo, do you have any comment about like?
Yeah, I think that we'll have to do it in some way, and it's kind of a natural consequence of what we are doing today in the mobile field, in the mobile area, because in the end, exposing hooks, hardware hooks to software is something that we absolutely need to do in the future, because that helps in many respects. Could be security, could be stability, could be energy efficiency, because as I said at the end of my presentation, context awareness is fundamental to maintain adequate energy efficiency, other than security and et cetera. So we're already doing this progressively in mobile devices. We are not there yet, of course. So it will take a while before we get a really fully connected stack from circuit up to software. But we are progressively getting closer. And certainly, we will have to do the same, the IoT, and even more so because we are more constrained. So I totally agree. And this is something that we don't have to think about. We just have to do it in the most efficient possible way.
Okay, next question.
Sure. Just a comment as we're talking about the security on IoT devices, that my Nest thermostat seems to know everything I'm doing in my house. And I'm wondering if one of these days it's going to be hacked. And when I go and say, turn up the temperature or turn down the temperature, it's like, I'm sorry, Nathan, I can't do that. A la hell. But my question is on an 11AH. Two questions, actually. One, you talked about the ability to cover the yard outside very easily. My question is, at the other end, what's the sensitivity to 11AH in terms of being able to penetrate walls?
Well, it's better than the higher frequency bands like 2.4. I mean, that's what you get with the lower frequency. So yes, it will go through walls more effectively than the 2.4 gigahertz frequencies.
So
you're worried about security and getting out to your neighbors?
No, but so it should be much better then. And will that vary with concrete versus drywall?
Yes.
Okay. Yes. And secondly, you did a hand wave about talking about the fact that the spectrum assignments were different around the world.
Right.
I think a lot of us are spoiled by 802.11, A, B, N, whatever. And Bluetooth, where pretty much you can ship a worldwide product and not have to worry about those spectrum assignments. So how do you build a SKU that can be shipped around the world if you have different frequency bands that are going to be used with that protocol?
Well, it's just a matter of having a flexible radio that covers those bands. And then you have to, there are ways to enable those bands, by country, which is actually done now in the chips, because you can't, even though in the 2.4 gig band and 5 gig band, different countries have different power limits, for example, and different spectral mass requirements. So all of that's built in, and you just have to do a one-time programming effort to make sure for the given countries it's supported properly. So we can take care of that. That's not a big problem.
So if I take the router that I bought in the U.S. and I try to plug it in Germany, will my router today adapt to the different German standards?
It depends how it's designed. It could do that, yes.
How would it even know where it was?
Well, there might have to be a setup process where you do that.
Okay. So, thank you.
Yeah.
Okay, I think we have maybe one more. Okay, maybe two.
My question is about the mesh protocol as opposed to the hub and spoke. So my question, when you are talking about sleepy devices, how does mesh protocol even work with that? Somehow it looks very counterproductive, counterintuitive, sorry. That when you have sleepy devices, but we are talking about mesh protocol, whereas normal life enterprise network, where all the devices are powered up, but we know that things have evolved into a hub and spoke technology. So could somebody comment on that?
Yeah, that's the function of that proxy I was talking about. So there's a piece of software sitting in the middle that does the protocol translation between the RESTful side facing toward the application and the constrained side facing toward the device. And you're right, the way that communication works is dramatically different. So what that software does is it's got some storage built in there. It's got, it has a resource database. It knows who it's talking to or which devices it's talking to, maintains a history of the resources that are out there. And so if a RESTful call comes in and says, what's the temperature? And the thermostat or the thermometer is asleep, it can do several things. It can immediately respond, well, it was 73 degrees last time I looked, or last time the thermometer reported. Or if the application wants the temperature like right now, it can say, the proxy says, well, sorry, the thing is asleep, but I'm gonna let you know when the thing wakes up and gives us a new reading.
But does Nest do it right now?
Pardon me?
But Nest doesn't do it.
I can't. I don't know what Nest does. I'm just talking about the general case of the proxy-based translation between a RESTful interface and constrained device.
Actually, what you said that makes a lot of sense for the proxy-based, and so I don't have any. That is very understandable, intuitive. My question is the mesh protocol, which apparently is supposed to be used in house-wide network, that I'm finding counterintuitive how the mesh will work if the devices are sleepy. That was.
The what would work? I'm sorry, I'm having trouble hearing.
If the devices are sleepy, how the mesh protocol will work?
Are you asking about Nest, the thermostat?
No, mesh as opposed to spoke and hub. Because some of the
mesh. Yeah, we're not getting the sibilance here. I see what you mean. The mesh nodes, some of them are routing and some of them are non-routing. Does that help? The non-routing nodes are just end nodes, and then when they send data, it's the routing node's job to get the message for it to the network where it belongs. Is that what you're asking?
Yeah, basically, I was simply saying that in a home, hub and spoke seems to be better architecture as opposed to mesh.
I'm sorry, I really can't hear.
We can take it offline. Offline. I mean, we almost out of time. If the last question is a quick one, you can go ahead and ask.
Gary Fleeman, just asking, since it's a CHIPS conference, I have to ask a chip question. With the Internet of Things, life cycles are very short, product lines are very, very low cost, but yet we saw great material today with the power supply devices. So maybe, Mike, for you, in the Theros world of chip, how can the ASIC or infrastructure devices keep track or keep up with this tightly coupled optimization power that Massimo mentioned with the very quick changing, very quick ASICs and hardware? Is it going to keep up? I mean, how can we make the changes to ASICs and support to make up product cycles that short?
I'm not sure what you
if they're really tightly coupled, these are extremely low power situations. So if they're very tightly coupled, it seems like tightly coupled and fast cycle times don't necessarily go together in the chip business.
Right. Well, I mean, the different products, evolve at different rates. Like, access points and routers actually have a pretty short life cycle as well. And I think probably a lot of the IoE devices may as well. I mean, to some extent, that what you're asking is dependent on the nodes we have available and process nodes and the way that the IP is designed that we use.
Yeah, and my personal opinion is that power management will no longer, when things will be more mature, just chip-level power management. It will be distributed in a way, because devices need to talk and to adapt to the actual situation in which they are working, which means that actually devices at a higher level of hierarchy should be able to, through security protocols, of course, be able to change and give information about the most appropriate power management strategy, which might change over time, even faster than the pace of different generations of products. Even within the same generation, conditions might change. So if you're interested, you can have a look at an editorial paper that I wrote in TCAS 2, I think 2 years ago. It was December 2012, where I describe this kind of distributed power management. But certainly, it can't be just chip level. You're welcome.
Okay, thank you so much. And I think ends our session. Enjoy your reception, and see you all tomorrow.